Okay. Yeah. Am I audible on Zoom? Could people give a thumbs up if they can hear me? Okay. Okay. Perfect. Hello, everyone. Thanks for coming to this recitation and midterm review session. It'll be me, Sean, Aditya, Lucas, and Žiga who would be covering most of the topics that have been covered in class. And this is what the agenda looks like for today. First, we'll be covering some of the review stuff that was done in class, which was about, I think, 4 lectures. So that'll be the fundamentals. Then we'll be covering NLP. So that includes word embeddings, RNNs, LSTMs, and transformers. Then Lucas would be covering CNNs. Sean would be covering modern vision networks. And the generative models will be covered by Aditya and Žiga. Am I missing anyone? And Lucas. Okay. And between all of this, there should be a 10-minute break at about after 90 minutes, I think. So 7:30. And throughout the review, we'll be referencing prelim questions as we cover the topics. A quick disclaimer, topics covered are not indicative of the content that's going to be appearing on the midterm. You've done about 15 lectures of class, and we need to condense that into 3 hours. So there's a chance that some topics do not get covered, but you have the responsibility to study them by yourself. Also, do not interpret any questions or any material covered today as hints or suggestions for what's being asked on the midterm. Also, it's a long session, so I've got everyone chocolates. Okay, so starting off with the fundamentals, you guys already know what a you guys already know what a neuron is, and you know that connecting a lot of neurons together can form a neural net. You guys have also studied in class that the multiple layers in a neural net correspond to decision boundaries on your data set. The first linear layer was all of the linear decision boundaries, and the second linear layer was concatenate or connecting them and having a more complex decision boundary. These networks are also called feed-forward networks, and there's a variety of terms used for this: multi-layer perceptrons, feed-forward networks, and specifically feed-forward networks are what are being referenced in the transformer slides that are coming up in the future. So please remember that term. Quick tidbit is for a layer, the input layer, which has 2 neurons, and the hidden layer, which has 6 neurons, the weight matrix between these 2 layers would have the dimension of 2 by 6. And likewise, the other, okay. Is there a way to have my pointer on here? Do you know? Okay, never mind. So yeah, between the hidden layer and the second hidden layer, the dimension size should be 6 by 2. So whenever you'd encounter questions about parameters, count the number of parameters, this is what you need to pay attention to. What are the weights in your network? What are the filter sizes in your network? And they should give you the number of parameters. And this will be useful also in RNNs, which we'll also be covering. So the high-level structure of the fundamentals that we're going to be covering is as follows. First, the inputs. Second is the model. And finally, the output. Your inputs could be text, image, or audio, and each are pre-processed differently. Your model could be CNNs, transformers, RNNs, LSTMs, VAEs, and the list goes on. Just plug in your model. And after the output, what you've also studied are the loss functions. These are MSE, cross entropy, triplet Sinclair, reconstruction loss across all of the generative models, and the list goes on. So the way we'd be doing this is I'd be covering bits and pieces of all of these sections as a high-level overview, and we do a deep dive into the models.
I think we have to let people into the room, so you might want to make me host or something so I can let people in. So you first need to let me in this one. The participants have.
I don't. Oh.
I'll make co-host.
Do you see the recording sign?
Yes.
It is okay. 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 So beyond the high level structure, like I was saying, I'd be covering each section that we. Thank you. Is that okay? Perfect. I don't like this thing coming up in the middle. Sorry about that. Yeah, so I'd be covering each section at a high level, and then we'd be doing a deep dive into some of the models. So first off, starting with the loss functions, and this the flow is a bit different from how you've studied things in class, where your loss functions are all over the place. I've tried to condense them in one place, and this would be the theme across the fundamentals, where bits and pieces of lectures that have been done across the 15 classes that you've attended would be condensed in one place because some things relate to the other things right in the beginning. So starting with loss functions, obviously, what you need to understand about loss functions is that they measure the distance between your ideal distribution and whatever your model is modeling. So it also measures how likely or unlikely your data is, and the lower the loss, the better. In a regression setting, as you guys already know, the loss function that we use is the mean squared error. I'm not going to be going into that at all because that's the most straightforward loss function there is. However, I will be talking about cross entropy a little bit because the interpretation of it, I think, was not covered in depth as much. There are other loss functions that are also covered in the second half of the recitation. Oh my God, is this going to keep happening? Okay. So the mean squared error, among the two definitions that I've given you of loss functions, either measuring the distance from your ideal distribution of data or measuring how unlikely your data is, the mean squared error represents the distance. The cross entropy, however, represents the unlikelihood, and I'll explain in a bit what I mean by that. So this is the formula that has been given to you in class, and I'll admit it does look not as intuitive. So we're going to be trying to understand what that means. So as you know, after the softmax layer, which is the final layer of most of your models, you get some sort of a probability distribution of what the predicted label could be. And if that is the softmax output and the expected data is as given to you as 0, 1, 0, 0, how can we calculate the probability of getting this expected data? Any suggestions from you guys? And just to explain, we have the probabilities of each of those occurrences in Y0, Y1, Y2, Y3. Any takers? Yes. Right. That is exactly right. And what we'll be doing is doing a probability of not getting this label activated. So that's 0. Probability of getting this label activated. So that's against 1. Of not multiplied by not activating the third neuron and not activating the fourth neuron. As you know, we have the probability values, which are Y, and we also have the negative or the probability of not happening 1 minus Y, which is the yellow fields. And if we use each of these values wherever applicable, this is what the terms look like. So 1 minus Y0, Y1, 1 minus Y2, 1 minus Y3. When these get multiplied, you can think of them as multiplied and raised to the power of 1 because there's one of each, because there's one label against each of the expected data outputs. And then you can think of what this is raised to as simply using whatever is your expected label and using it in the sense either as 1 minus expected label where it's not happening, or directly the label, which is 1. And if you look closely at what this product looks like now, if you could simply use the log, since we do not do multiplication, since it's not tangible sometimes, we'll be doing a log. This equation of probabilities, which is your likelihood of your data, will look exactly like the equation that's been given to you in class. So that is what I meant by measuring the data likelihood of your expected data using the formula for cross entropy. So please always visualize cross entropy as measuring the likelihood or unlikelihood of your data. The reason I say likelihood or unlikelihood is because we have a negative sign. The negative sign is what makes it unlikelihood. So the more likely it is, so lower the error, the more negative this value is. So more positive just the log term is. That means the higher the probability of the data occurring. So higher the data likelihood. So that way, this cross entropy loss is a direct indication of the data likelihood. That covers the loss aspect. And we now know that the loss measures distance and unlikelihood. On the other end of the pipeline here, we have the input processing. The input processing, what we mean by that is inputs could be in varied forms. They could be text, images, and audio. These need to be encoded as numbers because obviously computers don't understand anything else. So when we have text, some of the forms that you guys have studied in class are one-hot encodings, bag-of-word representations, and obviously using the word-to-vec model to come up with hidden embeddings. As for images, obviously you can use the direct pixels, but as we've seen in class, these do not capture the semantic relationship between sections of the image. So we do the same process similar to word-to-vec, but our model this time is a CNN-based model, and then we use the final layer as a hidden feature layer. So in both cases, text and images, we come up with hidden embedding representations of our data. So that covers the input side of things. As for backpropagation, I believe everyone has been able to do questions on the homework and the midterm. So I wanted to do a pulse check as to how many people want backpropagation covered. Okay. Since it's only a few and we have a lot to cover, is it okay if we do it at the end? Okay. I think we'll do the question at the end as well. Moving on to optimization. So optimization, as you know, are the algorithms used in the optimization of your backpropagation. So you would want to backpropagate. Actually, before I say that, so for backpropagation, the only thing you need to remember for backpropagation is that it calculates derivatives with respect to losses. And like I said, like I've already shown you all of the losses, MSE, cross entropy, you need to be taking derivatives of that loss with respect to any of the parameters of your model. So that gives you calculation of derivatives, and then you use those derivatives to update your weight vectors. That's how learning happens in a model. Optimization helps this learning and makes it as optimal as possible. So some of the terminology that you might need to know before moving on is local minimas, global minimas, saddle points, and vanishing gradients. Is everyone comfortable with those terms? Okay. So starting off with gradient descent, like I said, the two steps in backpropagation are get the gradient and update the parameters. So this part is the gradient calculation, and updating the weights is updating the weights. And then together, this is how you backpropagate and do gradient descent. So gradient descent is essentially the algorithm that does the weight update and the learning of the model for you. However, there's an issue with gradient descent, is that it's compute expensive. where you have to consider every single point in your data set to compute the gradient calculation red parameter here, and that's pretty expensive. So what can be done better? We can do this stochastically, which means that we can only sample one point from our data set and then calculate the gradient based on just that one point, and then update the weight. But this still has an issue, is that because it's always taking one point from anywhere in the loss landscape, it's possible that it's going to be noisy around the minima, or it'll just never converge and it'll just keep bouncing around the minima. So that's bad. What else can we do? We can do a mini batch, so that way it's the best of both. It's not compute expensive, and you also get to do it slightly stochastically still. So you take a mini batch of all of your data points, calculate the gradient, and do the weight update. Okay. However, again, there's a problem with this, is that without any momentum, it's possible that it can get stuck in a saddle point. Does anyone want to give any inputs on why that can be? Yeah. Yeah. So yeah, the answer was there's not enough points sometimes in the mini batch that you have where you'd have a gradient calculation that can help you jump off of the saddle point. And then you're stuck there. So how can we improve this? And also just a brief note, although you are not expected to memorize all of these weight update rules, it is important that you understand the motivation for going from one optimization technique to another. So like we said, without momentum, it can get stuck in a saddle point. So how can we resolve this? Obviously, we'll be doing stochastic gradient descent with some momentum added. What that means is any gradients that you've had until now, until reaching the point where you were stuck at the saddle point, there will be some gradient accumulation that is maintained, and that is the term that is used to update the weights. However, again, this can get stuck in a saddle point if only certain dimensions of your gradient contribute to the gradient and others are completely zero. So it could be a saddle point along a dimension where there's no gradient signal. And that is something you would want to avoid. So how do we combat that? Actually, to clarify, think of them like dimensions. If there's two gradients, one in the X and the Y direction, if it's zero in the X direction, it could get stuck in a saddle point because of that. How would you combat that?
Bigger learning rate, smaller batch size.
Yes, but that could there could still be certain directions where if your gradients are completely sparse or they're like just zero, there's no signal or data coming in from, and then you're overfitting to just a few neurons. Is how else? So maybe that helps, but maybe not in this case. Anyone else? Yeah. Right. So, so as not to get stuck in a specific direction, you would want to do adaptive learning rates where both X and Y directions will have like separate gradient updates or gradient accumulations, and you can maintain those. 622, okay. So yeah, that's where Adhitya comes in. Here you're maintaining the second moments, so that's the GT squared. And you're doing element-wise multiplication. So that's the element-wise control, so that any weight vectors in different directions, X and Y, can be updated at different rates, which will be in GT. And GT is not just a constant, it's a vector where every dimension has its own gradient term. But the problem with this is that it can end up stopping early if the initial gradients are too high. What I mean by that is if for a certain direction, the GT squared term is like super high, the learning rate decay, because we're dividing by VT plus 1, is going to be high. So the learning rate is going to be super, super small. and then there's not going to be enough weight update in that direction. So there's a possibility that your backpropagation algorithm just converges at a non-minima. Okay, so this is how it gets over saddle points. But to get over stopping early, we use RMS prop so that if there's any gradients in the beginning that were super high that could lead to your weight decay being really high, you can control that by doing like an exponential moving average thing, where you can weigh the older gradients lower compared to the current gradient. Make a note that we're always in both AdaGrad and RMS prop, always just adding the second moments, which are GT squared terms. Even though the update term has GT, but the accumulation is always on the second moment. It helps to have the first moment so that the weight update takes into account all of these terms. So that's where Adam comes in. Yep. So Adam combines the benefits of both SGD with momentum and exponential decay. And that can be seen in the terms where you have the NT plus 1 term, which takes care of the first moments, and you have VT plus 1, which is always taking care of the second moment. And then everything else is pretty much the same. And that way you have both the moments taken into account. I think I'm gonna skip over Adam, but essentially the only difference with Adam W is that you add some L2 regularization. The reason I'm not covering in depth is I think I should cover regularization first. That being said, regularization. So this is a scenario where your training error is low and your test error is really high, and that is the overfitting regime. And regularization in particular helps you where your model needs to generalize more, and if it's overfit, it doesn't help you as much if it's underfit. So if you had to put a bottom line on like what regularization is, it ensures that your model doesn't overfit. And let's understand why overfitting even happens. And this is a very naive interpretation of why it happens. So think of your model like this, where the intensity of the color of the arrows represents the weight on it. So WI is the highest weight in between the second and the third layer. And say, for example, most of the weights connected to the first neuron, which is highlighted in black, are high. And everything else related to the second neuron are really, really low. So what's going to happen is your model is going to become super sensitive to any, and these could be any dimensions, by the way. So the first neuron could be talking about anything like color or shape. These are just examples. So for example, then in this case, your model is going to be super sensitive to any color in your input images or input data, or the shape, and the shape would have no sensitivity at all. So this is bad because then, like we said, the model is overfit and it's not going to generalize well, which is a really good property to have on your data set or model. Any questions so far? Okay. Okay. So ideally what we would like is an evenly distributed weights across all of the layers. So what are some techniques that I use to tackle this? First is early stopping. You can stop before it even has the time to become that specific and update the weights so much, so far that they get skewed. So that's early stopping. The other technique is L1 and L2 regularization. And I've put in intuitive visualization of what L1 and L2 regularization is like. So if you think of your bad model or the overfit model as the image on the left, also image courtesy Sophia, whoever they are on the internet. So as you can see, if you think of each spike as a different dimension, and if you think of each spike as representing a different dimension of your weight or a different weight, the weights are all over the place. So what L1 and L2 regularization try to do is try to simplify your weights as much as possible and try to have them lie on a smoother surface. So L2 looks spherical, and obviously L1 looks linear because of the nature of the gradient updates, which are square terms and linear terms. The third technique that helps with regularization is dropout. Dropout, I know there was a bit of confusion in class where what dropout represents. So on the exams, like, be on the lookout for, or ask if it's not mentioned, what dropout represents. It could either mean the number of neurons that are dropped or the number of neurons that are kept in the model. So the definition can vary across, but we'll try to stay consistent throughout this class as dropout being the number of neurons or the percentage of neurons that are dropped. And that's what you implemented in P1, I think. So what dropout does is it ensures that there's no overdependence on specific neurons by deactivating them during, yes, question?
Dropout, like you said, during train time, we essentially remove neurons with probability P.
Yeah.
And at test time, we have to one slide said multiply by P.
Mm-hmm.
The next set of slides said multiply by 1 minus P.
Yes.
Which is the right definition given
yes.
the case that you just described.
Yes, I've put that on the slide and be there in 30 seconds. So for this slide or this recitation, the dropout rate is the percentage of neurons that are dropped from the network. And with that in mind, and that is exactly the thing that you guys have implemented in P1. And I think this is what was on the slides, but we discourage you from this. Okay, sorry. Yeah, so the final directive on that is either you divide by 1 minus P in the training term, or you can multiply by 1 minus P in test time. And I think I forgot to add a cross on there, so I'll just remove it. So that's the final directive then. Does that answer your question? Okay. The other two techniques are increased learning rate or skip connections. How does increased learning rate help? It helps because you'll have noisier updates. If your learning rate is really high, you're going to be jumping around the loss landscape. So that leads to noisier updates. And stochastically, more of the loss landscape is accounted for when you're doing gradient calculations in your mini batch gradient descent. So in some ways, this helps the generalization of your model. Skip connections, which you guys covered as part of ResNet, were not mentioned, I think, as a regularization property or something that helps regularization. But skip connections, in fact, do help regularization. And the reason for that is, for example, in the residual blocks that you see on your screens, on the screen, if f prime x, which is the derivative of, say, f is the loss function, if the derivative vanishes, the skip connection helps it not vanish. But if it did vanish, what would happen is only certain weights or certain neurons are technically deactivated and not taken into consideration for your model inference. And that also, again, leads to this property of sensitivity, where the shape neuron was like completely deactivated and the color one was highly, highly activated. And like we said, this is what we want to avoid. Okay. So adding the 1, so even if f prime of x, the derivative vanishes, tries to vanish, adding the 1 from the skip connection helps maintain the gradient, so to say. So the gradient that otherwise would have vanished is maintained. Next, we have batch norm and layer norm. In class, I think this was covered as part of your CNN lectures, but batch norm and layer norms are also what do I call them? Are steps used to regularize your model. So batch norm, as you can see, given a batch, you take the mean of the batch, and that's a standard Z norm. You subtract the mean and divide by the standard deviation, and that should normalize your data across the batch dimension. However, as you can see that it needs to take a sum over all of the data points. So this can only happen at train time and doesn't happen at test time. So what instead needs to be done at test time is you need to maintain a running average of any data points that you've seen along the way. This is how batch norm looks across fully connected networks, so MLPs and CNNs. Always make note of the dimensions that have been given to you, and whichever is the batch dimension, that's what goes down to 1, because you're normalizing everything along that dimension and squishing it into one single value. So those are the shape transformations. And batch normalization for convolutional networks where you have batch size, channels, height, and width. They need to be done across all of your data points. So in images, the data points are your pixels, and your pixels are in the height width dimension. So that's the shape transformation there. Then we have layer normalization. On the left is the original batch normalization for fully connected networks, where it's done along the n dimension. However, in layer norm, everything is done across the d dimension, where, as we saw for input processing, the text could be an embedding, images could be an embedding. So whatever length that embedding is, whatever size that embedding is, you do the normalization along that dimension. So this is going to be useful in transformers because, as you know, one of the layers in transformers is layer norm. So please make note. We also have instance normalization against batch normalization. So batch normalization of convolutional networks you already seen. Instance is where you only do it per image or per instance or per data sample in your dataset. These are the image representations of all of the norms. Do you have any questions on this? Yeah. I'd say, I believe mainly we use layer norm when it's text. Let me think. Any inputs? Think of it in maybe multi-head attention. So in multi-head attention, you split your head into, say, if the head size is 8. So that splits along the batch, along the D dimension. This is images, so forget this. So that splits it along the D dimension. So because of that, if you would do batch normalization in that case, you would be normalizing along values from other heads, which is a bad thing. So I guess it's very specific to the use case. Specifically in transformers, that is the reason why you do it along the layers. Yeah.
What is CNN?
Oh, convolutional neural networks.
Sorry, C here.
C means the channels and N means the batch size. So specifically for the first block, if C is the number of channels, there's a lot more channels there, but think of images as having 3 channels, R, G, and B. So there's different numbers for your image along the red channel, different numbers along the G and the B channels. So each of them can be represented along one channel, and your height and width, the reason why, even though height and width are 2, and there's only like 3, this is only a 3-dimensional cube, is because your height and width are concatenated one after the other and just made into a flat vector. Does that make sense? Okay. Okay. So this ends the fundamentals and the review part of, and I've summarized all of this as few short principles. This really does not mean anything in machine learning or deep learning. I'm just coining this because I think that these are principles that if you know, even if you forget everything else from this class, just remember these things, and then you can pick up and wherever you left off and just revisit everything. So that is inputs, need, encoding. Your training or learning happens whenever your weights or parameters or kernel filters get updated. That happens through backpropagation. And to do backpropagation, you need a loss function. The loss, like we said, it either measures distance from your ideal distribution, or it measures the unlikelihood. The purpose of training is to maximize the likelihood of the data that you're training with. So that's the distribution that you're training with. And ideally, there's no covariate shift or anything, and your test distribution is still the same. So you want to learn the distribution of your data as part of your training. Optimization algorithms help backpropagate and reach a lower loss optimally, and regularization ensures that you do not overfit. So these 6 principles, I'd say, they prime you to understand deep learning, and no matter whatever domain you study, either the inputs change, output change, inputs change, or your model changes, or your loss changes, but the fundamentals remain the same, that you use the loss to backpropagate and learn and train. With that, I think we are ready to now dive into some of the models. Before I move on, any questions so far? Okay. Any suggestions? Am I going too fast, too slow? Okay. Oh, yes.
Why it's 10 by 1 and like what that is actually doing.
So think of it like text samples, maybe. So n is the number of is their sequence length, or the number of words that have been embedded, and each word has been embedded with a d-dimensional vector. So when you're doing a layer norm, you're doing normalization along the d-dimension of each sample. So you're normalizing each sample to get a value, normalized value at that layer, along that, what do I call it? Along that embedding, sorry. So for each word, along the dimensions that, along the embedding dimension, you're going to be normalizing everything, and you get one normalization term along that dimension that's going to be used later. So that's just the mu and the sigma. Sorry, let me explain here. So you have cat and mat, and you have a 3-dimensional embedding for each. Along the 3 dimensions, you need some mu and sigma, right? Because you have some values A, B, C, D, E, F, and you want to normalize each of these. So you're going to use A, B, C by 3 to get mu. So that's one value for a 3-dimensional embedding. So that's the mu and the sigma becoming. So you do that for each of the samples. So it becomes n, which is 2, by one value each. So 1. Does that make sense?
Yeah.
Okay. Those are just the values used for doing the normalization, by the way. Your actual data remains the same shape, n by d. Okay. Okay. I apologize in advance, since this part of the slides that I'm covering, I have not been able to make the slides to my liking. So some parts I think I'll try to explain on the board, so try to accommodate. Okay. Although I think if I turn my camera on the Zoom, people might be able to see this board. Okay, okay. Okay. Might take 1 minute. Okay, let's take a 30-second break. Yeah.
Can I ask a question about like batch norm and instance norm? So in what, it said on the slide that both of them are CNNs, and like what circumstance do you want to use the batch norm for instance norm?
Honestly, instance norm, I'm not sure where I should, I would think maybe instances like Sinclair, where you're doing stuff only relevant to one image at a time, one image and its augmentation, maybe, but that's just me speculating. I don't know the exact answer for you, but we'll make note of that and try to think why. You can ask.
We usually use instance norm when we want to normalize each independent feature in a sample, as opposed to normalize everything across the batch.
So the answer here was you use instance norm when you want to normalize each instance of your data. But a specific example or a scenario where it's used, we'll get back to you on that. Thank you so much. Okay, so now we're moving into the NLP section of the review. This is where we are going to be covering word embeddings, RNNs, LSTMs, and transformers. As you can tell by the topics listed, there's a bunch that we've completely not covered. So things like dense nets, Google the nets. It just given the time constraint, we've just dropped those, but you should refer to whatever was covered in class and not much more. So starting with word embeddings, yes. Oh, these ones? Okay. Are you guys good with posting these slides?
Yeah. Right now, the link is on editing. So, like, I managed to do that link. So, if you post it, then people will edit it.
Oh.
We'll post it afterwards.
Okay. No, I'll just post a PDF of the current version. I won't post the slides.
Okay.
No, that's fine.
Oh, you can I can do that.
Yeah, but it's being updated on the fly. I just don't want to deal with that. Okay, you should have it now. Oh, this is what I was trying to. But yeah, this is the updated slide from class about dropout, where you multiply by 1 minus p at test time, in case anyone wanted. Okay. So word embeddings. Okay, before I move on, a lot of the things that we covered in the fundamentals about the loss functions, the weight updates, is what is considered, might get glossed over in here, because my understanding is now that you understand those aspects, we'll not dive deeper into each of the loss functions that come up with anything like skipgram or CBOW models. So when I say loss functions, I'll show you what the loss function is, but now you know that it encodes the likelihood or unlikelihood and directly move on to the concepts and high-level concepts across the models. So the word embeddings, as you guys might remember, I guess, are motivated by semantic similarity. So all of the text, taking text here, obviously, for example, so all of the text needs to be encoded into a space such that there is a directional value to the encoding. What I mean by that is the dimensions in which the encoded text lies has certain concepts along certain directions. So along the X direction, it could mean color, which was previously on the neurons, if you can relate to that. So there's some parallelism there. So along one dimension, it could mean color. Along the other dimension, it could mean shape. Along some other direction, it could mean gender, royalty, politics, and the list goes on. So, which is why I guess in the recent models, the embedding sizes are so huge, is because there's just so many concepts to encode. Given that, what we want to do is try to come up with this space of embeddings where concepts lie along certain directions. And the first model that was introduced to you that does that is word2vec. There's two variants of word2vec. One is the skipgram model, and the other is the continuous bag of words. The only difference between the two is that the skipgram predicts the context that lies around a target word, and the CBA model predicts the target from the context. And that is just the training. That is just how the training is going to be set up. What exactly gets used is going to be the weight matrices to generate the embeddings, and we'll get into that. First off, what is your training data when you're dealing with this model? It is one-hot encoded vectors of all of the words in your vocabulary. And you guys have already covered this as part of the input processing, where input processing can be one-hot encoded, bag of words, or hidden dimensions. And we're trying to get from one-hot encoded to the hidden dimension. So for that, also, again, the images used here are the ones from class. I know there's images that were updated for you on the homework based on along which dimension the actual embedding lies. But I always, no matter what the shapes of the matrices that's given to you, a good indication is always to look at what is the vocabulary size dimension and what is the other dimension. Obviously, the one that is the size of your vocabulary is going to represent words along that dimension. So because this is size V, each row is going to be an encoded embedding. Same goes in this, where since this is the vocabulary dimension or vocabulary size dimension, everything is along the columns. So that's always a good indication. So you start with your one-hot encoding. If you look at your one-hot encoding vector, and if you do a dot product with along the dimensions, so these are this is going to be mod V dimensional because there's that many terms in your vocabulary. So if you one-hot encode, say, five words, this is going to be 5-dimensional. So think of this as 5-dimensional, and that gets cross-multiplied with this, and then whichever is going to be the row against which you see a 1, the one-hot encoding is going to be picked out, and that's going to be your hidden dimension. Is that clear? Okay. Once you do that, you are going to try to align or like reshape your hidden dimension, hidden embedding vector back to your original vector. Back to the same size as your original dimensions, which was mod B. And can anyone think of why we're doing this reshaping? Like we're going down and then going back up. Mm-hmm. Yes, but why specifically mod B then? Why not? If this is D, why isn't this like D2 or something? Yeah. Yeah. Yes. Perfect. Yeah. So the answer was the reason this is again mod B is because all of our input as you recall the training data slide, all of our input is one hot encoded vectors. So the way you'll interpret whatever gets decoded here is going to again be mapped to our original data. So here you're going to get some kind of values. And that's when you use your ground truth. So again, going back to the fundamental slide where this was your output softmax, and these were your one hot encoded vectors. So this embedding of cup is already in your data set. So now what you just need to do is try to get a cross entropy loss between what has been predicted versus what is the ground truth, and try to maximize the likelihood of this being your ground truth. So you're trying to get them close together as much as possible. So minimize the loss. Yeah.
So for skip graph, if you have two context words in either direction, and let's say we have copy, do this for each of those 4 words and just do the same thing.
Yes, so it'll do it 4 times. It won't do it parallelly. It'll do it one at a time. And yeah, so then you do the cross entropy loss. And again, you take calculate gradients of that loss and do weight updates. So can anyone tell me what the weight updates in this model are, or what the parameters are? Yes. Yes. So those are the things that get updated, and those are your training parameters or learning parameters. You call them different terms. So yeah, do a forward prop, reduce the dimension, increase the dimension, do a cross entropy because that's your training data, take a gradient, back propagate, update your weights, and your model is, as it does this along all of the data points in your training data set, you get more and more information about your training distribution, and you're trying to increase the likelihood of everything by using the cross entropy loss. So the purpose of the model is to align your model as much as possible to the real world distribution, if that makes sense. This is the CBAW model, which kind of does a reverse thing where it takes words in the context and predicts the target word. Again, cross entropy, you guys know what it is. Even though this says, oh, I think this image is missing one thing. So we had a question about whether this happens sequentially or parallelly in skipgram. So skipgram was one at a time. In the CBAW model, all of these, although not parallel, they do happen at the same time. So there's going to be like, if there's like 2 context words, there's going to be 2 embeddings that are pulled out of these, and they'll be averaged, and the average is what the hidden dimension vector is. So I think the average is missing in this image. And again, reshape it back and take the cross entropy loss, gradient, back propagate, learn. And finally, whatever you're left with is going to be your embedding converter weight matrix. So after your training is done, just drop everything else and just take this matrix W and use it to encode your text. And that could be any text, as long as it's in your vocabulary during training. With that, we'll be transitioning to RNNs. Is everything clear so far? Okay. Okay, so this is where the slides get a little, so just ask me questions wherever possible. Yes.
So I'm doing the skipgram and CBAW, what is inside the matrix W is what becomes the embeddings of the words.
You could say that, yes, because your actual input is one hot encoded, you could consider it as that. If it was like some other dimensional, if you were trying to convert from D to some D2, and then you had some matrix in the middle, you would say that you are encoding from one latent space to another latent space. But in this case, because our input is one hot encoded, every row is the actual embedding. So you're right on that. No, it doesn't. Okay. So we'll be transitioning to RNNs. So let's take an example where we have a single word and we have a single output that is being predicted from that word. And let's consider this is your model, and that has been just appended a little bit and flipped on its head and stringed together, where X is your input, H is your hidden dimension, Y is your output. And I'm telling you that your input dimension, so for example, the word cat is D-dimensional. Consider the hidden dimension to be H. Can you tell me what the sizes of each of these weight matrices is going to be? Output is 2-dimensional, say. So it goes D, H, and 2. Could anyone tell me the size of the matrices? And you get this.
D by 2,
Which one?
the weight.
There's 2 matrices. So there's one that gets, so if you see this model, think of that as being like flipped on its head and just vertical, made vertical. So this is one matrix, this is the other. This is your Xi, Hi, Yi. Flipped on its head, there are 2 matrices. Which one is your matrix? Okay. Yeah. Sorry, one sec. Someone's answering. Yeah. D by H and H by, this is 2-dimensional. Yes. Yeah. And your question was, sorry? Okay. Hidden dimension is H, input is D, output is Y. So does that make sense to everyone why that is? This matrix is going to be D by H, and this matrix is going to be H by 2. And I can clarify if it's not clear. Okay. Could everyone give me a thumbs up if they've understood why? Okay, thank you. So that was one. Oh, yes. Uh-huh.
You said that, when you say the weight
That was D by H.
D was the,
Oh yeah, it was. I'm sorry. I've overused the term a little bit. Maybe consider it X then. And I'm just using different terms. It's unrelated. I'm using different terms here. Okay, sorry for the confusion. Okay, to reiterate then, let's say this is M-dimensional. The input is M-dimensional. The hidden dimension is still D. Output is 2-dimensional. This matrix is going to be M by D. This matrix is going to be D by 2. Does that work? Okay, thank you.
I have a question. Why is it the other way around? Why isn't it M by D? Why is it D by M?
If you look at how it's structured as when it's an MLP, so again, ignore the term D here. The input is M-dimensional. So every dimension of the input needs to be connected with one neuron, with each neuron. So everything is connected. So basically you're trying to get a one-to-one mapping from everything in the input to everything in the hidden layer. And that's why this thing will have 3 connections, so 3 weights. It's the same thing for every row. So it's going to be D times 3. Does that make sense? So yeah, so that was the appended single word neuron model. And what the RNN does is, because it's recurrent, it just patches all of these together, and everything that is hidden also gets appended to the next hidden state. I think at this point, there could be a question as to what does H0 start with? You know that W1 or X1 is the word embedding. Also make note that in the previous slide, this is X1. In this slide, it's W1, which means that a word-to-vec model has already been, or a word-to-vec model's matrix has already been used to convert your X to W, or a word embedding. So to go from one hot encoded to a hidden space embedding. I hope that's clear. So yeah, back to the question, what is H0 to begin with?
Randomly initialize like values or like vectors.
Yeah. So theoretically, yes. I think in practice, where you've implemented LSTM in assignment 2, if you look at the LSTM implementation in PyTorch, the default values are zeros. So beyond RNNs, you will also have certain states like C zeros in LSTM. In practice, they're all initialized to 0. Okay, yeah. So with that in mind, every hidden state takes input of the previous hidden state and the current weight vector, and gives you some output. Again, whatever this output is, you will have your feed-forward network beyond this, or like you can consider this your feed-forward network, but whatever your output is, you'll always compare it with your expected data, take a cross-entropy loss, take a gradient, backpropagate, learn. Okay, I'm gonna say that multiple times, so don't be bothered. But essentially, it's just a way to model things. The reason why it's done this way is to somehow embed the meaning of a sequence or a sentence, where previously we were just going from a word to a word and a word to maybe a context word within a certain window. But with this, there is a sequence that is encoded within the model itself of word order, I guess. So yeah, this is the unrolled version and this is the rolled version. How would you say you will parameterize this model? By that, I mean, where do the weights lie?
One from W to H, one between the hidden states and one from H to Y.
Yes, exactly. So that's how you would parameterize, and you can put one weight vector. And again, we looked at how the sizes are calculated. So if you say this is d-dimensional and this is d-dimensional, this is going to be d by d. This is going to be d by d. This is going to be d by 2, d by 2. And you can just imagine if you have so many weights across the entire model, this is a really expensive model to have because it's huge. So one solution that RNN has come up with is maybe try to have the same weight matrix wherever possible. So this can be correlated with how you did skipgram, where the weight matrix always remained the same, and it was your input and your output that changed, and that updated the weight matrix. So in essence, then, if you have the same weight matrix everywhere, you would be updating the same weight matrix instead of having multiple copies that update differently. Does that make sense? Okay. So that's what this is about, where your yi is m multiplied by h, and your hidden states are always the combination of two things, which is w times h, so w is along this dimension, and u times vi, so that's, again, I don't know why we went from w to v, but ignore that. And then obviously activation function, and then you get the next hidden state. So those are the only two things happening in an RNN. Again, some issues with an RNN are obviously everything happens sequentially. So depending on how long your sequence is, this needs to happen one at a time for each word, if I think about it. So it's like super slow. So that's the issue with RNNs. And I'm not going into depth about the backpropagation in RNNs. Maybe if we have time left at the end. But that is it for RNNs. Any questions? Okay, moving on to LSTMs. So as you can see in RNNs, what can end up happening is as one word keeps going through this long sequence, we could again run into the problem of vanishing gradients, where because these gradients are already floating point numbers, they're small, and if they end up being small throughout, the signal gets lost, and there's less learning as you progress through the model. So that's the issue with the long context in RNNs that LSTM sort of tries to solve. So the way it tries to solve that is by adding this additional cell state, as it calls it, where technically there's not much learning happening along that dimension. It's just maintaining some data. So if you had to unfold this and think of this in terms of RNNs, this would be like you're adding some C neuron somewhere, and then C1 goes to C2, but it's just like a direct pass. It doesn't need to go through any of the other terms. Obviously, there's stuff that gets added, but that's just changing how the values of C1 are impacted, or there's no conversion happening from one embedding space to another embedding space. It's just that whatever C starts with, it'll either be zeroed out along certain dimensions, or it'll be given more information to carry along in its existing dimensions. Sorry if that was a bit confusing. Again, slides are not up to par here. But any doubts on that statement? Okay. So yeah, if you had to think of how this looks like when an RNN is updated, this is maintaining a C1 to C2. And think of these multiplication additions that are happening along the way between its conversion from the previous cell state to the next cell state as some kind of knobs and switches, where if you think of this like plumbing, and there's multiple hoses there or something along each dimension, you get to turn off certain dimensions by turning off the knob or switch along that dimension and not let any liquid flow through those dimensions, essentially. Yes.
Are you still taking gradients with respect to C?
I think we are, yes.
So-
Although, actually, no, because there's no weight updates along the dimension.
Yeah, well, I will add that C does play a role and it does get updated. It's grayed out right now. But if you notice, actually, I'll walk over here.
Mm-hmm.
We have this section where the C actually would pass back into the network and all those other operations. So the kind of output that gets output at each iteration, this is kind of its memory. So it's just saying, at this iteration, there were things here that I'd like to keep remembering or not keep remembering. So the updates don't necessarily go through like all of these non-linearities. It's just kind of a really simple way that it can keep track of its own state for each. But otherwise, it's just yeah, it's just keeping from one state to the other, and it's referenced during this computation of the H2.
Why is there two outputs at H2?
So you want to keep your hidden state, but you also want your hidden state to, I guess there would be a few reasons.
No, I think it's just.
Usually you would just have one HP. So I think what they're saying here is probably in a case where you're about to build into either an RNN that has multiple ways to look back at itself. So you can sometimes see these like two-dimensional RNNs where the hidden states.
No, I don't think so. Because if you look at the RNNs,
I think they did that whole last year.
so if you see this H is just going to the next hidden state here. So it'll just go to the next cell. This H is your output, which you can technically.
There's usually some ones where they actually have like another row of hidden states beyond. Or at least
Oh,
they covered,
multiples?
yeah, they covered.
No, I don't think we have that in.
Okay, this diagram might have been taken from a place where there actually were like a multiple dimensions of hidden states. But yeah, I guess you don't really need to pay attention to this output here. This doesn't really get used in the RNNs we talked about.
Yes.
Are you expected to memorize the internal structure of itself?
No, if there's any reference to the structure, you would be given the structure in the question.
Some things that we might want you to know are just maybe the vague ideas of what these states do. So the functionality of having a way to pass memory between one cell and another, versus some of the ways that the nonlinearity are applied. But we won't expect you to be able to like diagram this out. Just knowing that there's like a functionality for memory and then a like ability to produce this next hidden state is all.
Yes. Sorry, could you repeat that?
Yeah, it's like the fundamental.
I think they're just terminologies, but when you're when you would be adding like a feed-forward network for prediction. So for example, this would be some dimensional, and then you need to convert it to your output word embedding. So you would need to attach like a feed-forward network beyond the output. In that case, it's more so the hidden embedding, a hidden state that captures the embedding or the semantic information in your text. So the hidden state here gets used more if you need to use your model for anything. The cell state is, again, if you see the connection, it's also contributing to the hidden state, but throughout the network, it's just maintaining some memory.
I think also what you could say there is that they actually have a kind of similar role. It's just that the cell state is kind of information for the next state, whereas HT needs to produce a valid output now. So I think that's probably the main difference there, but they're pretty similar.
And just to clarify, are you learning anything for the memory, or is these all like hyperparameters?
You would be learning these, it would learn this, yeah, the gradients would come through here.
I'm covering the equations for this in the next 2-3 slides, and you'll see where the weight updates are. So that'll help.
So I know you said the Y's would be like past to like some linear like your embeddings or something. Are the Y's not already embedding? Or like how does that?
No, so sure, if Y's are the embeddings, but if you want to do like a classification task, so for example, your Y captures the embedding of what the word is. So for example, here, it's cat and mat, or let's change it to dog. So if you wanted to run a classifier on top of this RNN, you would have to consider this to be the output to a feed-forward network that converts, if the Y was d-dimensional, you need to convert it to 2-dimensional. So think back to the first neural network that I showed in the fundamental slide, where you went from 6 to 2 to 1. So you need to convert whatever Y is into classes. So if you wanted to do a classification using LSTM, you'd essentially have to attach some kind of a network beyond it.
That's for like specifically classification task, not something like you're generating the next word.
No.
You could just go from the embedding to the.
Yeah.
Okay.
Yeah. Any other questions?
What is exactly the asking? The difference on typing output or training?
Sorry, could you repeat your question?
What's exactly how we
So the cell state represents like long-term memory and the hidden state, because the cell state, you can only like add to it and subtract from it. So, or you can only add to it or conduct like element-wise multiplication, so it does not have vanishing gradient as in what that hidden state is. Because the hidden state, in order to remember something, you have to have the way to like literally multiply every single time. Does that make sense?
Also, it'll just be a vector. I don't think it has, since it's, if you look at multiplied and as we go through the next few slides, this might become clearer, is that you're either multiplying this, so if C was 3-dimensional and it has A, B, and C as the values, what you're multiplying is essentially a mask, which tells it, do you want to keep A, do you want to keep B, do you want to keep C? And what you're adding is some other information from the previous hidden state. The previous hidden state could have some latent embedding information of your text, and that gets added to this, which means that this originally to begin with did not have any memory, and now it is it's like a storage space to hold some information about the current hidden state. Does that make sense? Any other questions? Okay, and I think it will become more clear as I show you where the weights are and what gets updated. So moving on to the next thing is this part. Hold on. Oh, yeah. So yeah, this part that gets multiplied with your cell state has a weight matrix WF alongside it. Although the location here is shown here, but it's actually here. So your weight WF is going to be multiplied with this and both of the previous hidden state encoding and your input encoding, and that gets converted into something, and then some bias is added on top of it. So you can think of this as blocking certain dimensions, and I think I already explained this with the knobs and switches and plumbing example, but because you're multiplying, certain dimensions will get multiplied by really small values and they go down to 0. Certain dimensions will become really high. So the plumbing is open along those dimensions. So the first weight vector that we're getting, weight matrix that we're getting in LSTM is along this forget gate. So because it controls what the memory, so think of C as memory of your LSTM. What do you want to forget from your memory and what do you want to retain? That's why this is called the forget gate. Is that clear? Moving on, we have the input gate. Here we have separate weight matrices that get multiplied by xt and ht minus 1. And you can look at which one is which by looking at the equations. Sorry, I take that back. It's not separate weight matrices for both. So both of them get multiplied by both of them, and you have two separate outputs when you have, and this is, I think, the concatenated embedding of H's and input embeddings, if that makes sense. So that gets multiplied by both the matrices. You have two different types of outputs that again get multiplied. Again, I don't know why it gets multiplied before it gets added. I'll probably look into it and make a net post. But essentially what this is doing is it's encoding whatever was until now in your hidden state or some semantic understanding that you have captured in your hidden state until now with your current input. And as you add that and you store that in memory along the cell state. Does that make sense? So I guess the term I've put here is what info from my current input am I adding to the old state or old memory? Mm-hmm.
Okay, sure.
Why are you using the activation function? Like, what's the logic in the activation function?
I think it's the same thing that's been the case along all of the models that we've seen so far, is to introduce some kind of nonlinearity. Oh, that is a good question. I haven't looked into this. I had the same question too, though, but I can check and get back. Žiga, could you make or Lucas, could you make a note of that question? The question was why tan H and sigmoid both? Why couldn't it be like both sigmoid or both tan H type? What's the purpose of using different activation functions?
Yeah.
So,
Negative.
okay. Oh. Okay.
You have a question?
I was gonna guess what it would be. It's because the CL sigma is forget gate there. So it tells it what to forget and then what's good there is H is what you said, negative 1 to 1. So it isolates what's good and then multiplies it together and then adds it to the memory.
Yeah, I guess all of the interpretations sound equally good, so.
But yeah, the actual interpretation, maybe I'll make a post about.
How do we maintain the dimension of each who's impacting S3 or using the time for
So H isn't actually changing in dimension each time. It would just happen to be the case that the cell state might be more, or its dimension just might not be the same as the hidden state here, I guess. So when you're concatenating the input at that state with the hidden state, you would just have that be the dimension of your cell state, perhaps. Of course, it could be larger or smaller, but for the most part, that just seems like a pretty natural way to have it work. Is each state, your cell state's gonna like notice something about the current input and the current hidden state. So yeah, it would just be H and is gonna stay the same each time, but the cell state, actually the cell state will also.
But that is a good question as to how it expands and goes back to its original size. I'll take a look at the implementation for you. Yeah. Moving on. Yeah, like we said, multiply, forget irrelevant information, and add any new information. So that is the update state again. You can look at the equations. The final thing that happens is, again, you're multiplying. This is basically what your RNN was, but you're using your cell state to update your hidden state as well. So you're just maintaining the semantic information that was prioritized in your memory in your next hidden state, if that makes sense.
If we could stop there. Actually, it does seem like there might be a little bit of an inconsistency here with the shapes now that we go through and look here, because theoretically the cell state would be the same shape as the hidden state here. So maybe there's some sort of like way that they're kind of just treating them both as if they were concatenated, but then we only keep the hidden state section each time. But yeah, it does look like there's that this is either not concatenation or there's some way that we're indexing more smartly here.
Yeah. It's possible it's addition, but we'll have to take a look. We'll have to take a look. Yeah.
It's not.
No idea.
As a shape, yeah, shape will be the same.
I think all of the matrices will have the same shape because it's always the same thing.
Well, it could theoretically project from the cell state to the hidden state, but then we don't have a way that's in here that we can see that project back and so on. So, yeah.
Okay, it's okay. It's okay. Let's move on.
We'll make a post on LSTMs and like what this syntax actually means.
Yes. Again, performs better with long sequences because it now has a memory component, but everything is still sequential, which is why we need transformers. And this is just about bidirectional LSTMs, but it's about maintaining context along both directions, but we can ignore that for now. And
so just for, or one more forward with the bidirectional, just for completeness, I guess, this is kind of where the hidden state going up, like referred to. Whenever you have these like bidirectional, that hidden state does get emitted, but in a way that's not an output. I just wanted to make that kind of clear with like this diagram with what you mentioned earlier.
yeah, these green lines here. Oh, sorry, this black. Yeah, there was a question.
Yeah, so I would say that like this is at a high level, I say this cell state that is meant to remember information that's like made up of, you know,
Yes, yes, yes. And maybe also look into the dimensions of the weight matrices. I'm sorry, I didn't cover that. Yeah, transformers. We're already at 7:30.
That's good. We're on, I think we're making good time.
Is it? I was supposed to complete transformers by now, but we can take a break now if you guys want, or after transformers. What do you guys prefer?
Do you guys even want to break?
Oh, yes, yes, yes.
Okay, so we looked it up quick, and just for clarity, we do actually get a concatenation here between the hidden state and inputs. So that concatenation is real. WO just projects it back down to the hidden state.
Does that answer your question? I'm trying this. Okay, so some of the things that I'm going to be covering in transformers is the positional encoding, and I think we didn't go into as much depth as we could have in class. Next is obviously the self-attention, and the feed-forward is basically just that. And like I'd mentioned in the fundamental slide, the feed-forward network from the first slide with the MLP was like a clue to what's being used in the transformers. So that's the feed-forward network, so we won't go much into detail about that. It's basically just going to be multiple layers that convert from one input dimension to another dimension, output dimension. We will briefly talk about the layer, how the layer norm looks like within the encoder. And I think that is about it. There is cross attention too, but I think it's basically the same, fundamentally the same thing as what happens in attention, just that it's across the embeddings in the encoder versus the decoder. Okay. Starting with the positional embeddings. What you've seen in class or what you must have seen in your homework and projects are these formulae. I believe in the projects you were not asked to implement them. A lot of the implementation was given to you and you were asked to understand what they are. Could I get a show of hands how many people actually did try to dive deeper into what this is or how the equations work out? Good for you. Okay. So I'm guessing this should help. Again, the slides are a bit crude for this section, so I'm going to be using the board a lot. And for people on Zoom, well, it's background blurred. Does anyone know how I can change that without leaving? Oh, there you go. Okay. I hope you guys can see the board to some extent. I might not use it extensively, but I do need to use it. Yeah, so one thing that you guys have heard time and time again about transformers is that transformers do stuff parallelly. In RNNs, since the input was plugged into the network sequentially, the order of the sentence was maintained as part of how the input is processed. So there was information or positional information within the network just by the nature of how the model works. But in the case of transformers, everything is done parallelly. So any positional information from a sentence is lost or isn't utilized. So to counteract that, we need to add positional embeddings to the sentence. To explain this a little bit in diagram form, like we've talked, multiple dimensions represent different concepts. Some represent shape, some represent royalty, politics, blah, blah, blah. There could be, if you would have expanded your embedding dimension, which is your input, in this case, embedding, technically, if you were to expand it to add like one more D extra 1 and D extra 2, these could be like new dimensions in your embedding space that can capture, and if you put some positional information in here, that can capture positions. But in the case of transformers, the way it's done is, this is your input embedding. This could be D-dimensional. You generate a positional embedding, which is also D-dimensional. You add the two. And the expectation is that whatever positional information that you encode in the second vector, positional information of your input.
I got to go. It was like
You did? Oh my god, I don't know how I feel because
Whoever this is, could they please mute themselves? I can mute you too. But yeah, so the point is that you have an input embedding, but since the sentence is all in one go, the positional information is not there and you want to add it some way. Now we're going to dive deeper into a little bit about why these are sine and cosine functions. And to understand that, let's look at how how embeddings are essentially added. So if you had 7 positions, so consider that your sentence is actually 8. So consider your sequence length is 8. You want to encode all of your indices essentially as a one-hot vector in some way. Or like you need to have a unique representation for each position. Because otherwise, if the encoding for 2 and the encoding for 3 is the same, if you add, if the sentence is cat in a hat, and if 0, 1, 2, 3, if 2 and 3 have the same encoding, position encoding, adding them to a hat does not give any information about them being in the second and the third index. Does that make sense? So you technically want each of the position to be unique. However, as your sequence length gets larger and larger, you can imagine that this encoding is not tractable. Does that make sense?
I don't know, why are there 2 dimensions that you add instead of 1? And then,
Oh, that was just an example.
Oh.
You could technically have as many as you want. I think you can have as many as you needed to uniquely represent. So since if it's 2, you can uniquely represent 2 to the power 2 positions. Does that make sense?
Right.
If it were 0s and 1.
But we don't really actually do this concatenation. This would just be like, theoretically, you could try to do the positional embedding in this way. It's just for various reasons, I guess at the time, still now, people will do these embeddings by summing them over the entire vector. One kind of intuitive reason for that choice is that when you have, like, if you actually think about how you compute attention in the matrix multiplication there, having it in such a few number of dimensions makes it very like a sparse signal that doesn't actually affect a lot of values. So when you actually spread out that signal a lot more, it gives the model a lot more flexibility to interpret those actual positional embeddings as contextual. So they're like, they play a larger role in learning the representation of a word than if they were just nestled away in this tiny little corner of the vector.
Also, if you compare it to us going from a V dimension to a D dimension, so you're compressing your input words into a hidden space embedding. So you're compressing all of the information from across the words into some latent space that can represent all of your words in less dimensions. So technically, 2 dimensions could represent multiple dimensions. Think of it in a way like PCA way. So a lot of information could be about position could be encoded in just 2. This was just an example. I'm not saying this is done in practice. Did you have a follow-up?
what?
Did you have a follow-up question?
Why is it like, why do you need like cosine sine? Like, why is that?
Yeah, I'm getting to that. So that's one thing. So first thing is that each of our positions need to be uniquely encoded. Secondly, okay, this is a representation that I was talking about here, where certain dimensions could represent position. So if king and queen are close together, and also I'll share a link to this video, it's amazing. So if king and queen, if the sentence is queen and king, and you want to encode some kind of position into the embedding of queen, you technically want to push queen away from king, and did I say queen twice? Anyway, move queen away from king into a certain cluster that represents all of the words that come at the beginning of a sentence. So think of this cluster, maybe it has all of the articles in it, like a, the. So there's a position cluster somewhere, and you want to move queen and king, which are words in a sentence that are a bit apart, and you want to push them away such that they are in their respective clusters of position. Does that make sense? Mm-hmm. Yes. Oh, yes, yes, I'm going to go into the sign and costs of it here. Give me one sec. I'll come back to this.
When you do positional embeddings and you're pushing the vectors, the dimensions stay constant. That right? Or
Yeah. This remain constant. Yeah. Yeah. It's the same dimension. So maybe the intuition is that there's so many dimensions that some dimensions do encode position or like direction of sentences. So that's what we are trying to do with the positional encoding. Some properties that we want in this position encoding are that every position should have a unique identifier. We've already gone over that. Again, every encoding needs to be independent of the input. So if this is the position encoding that gets added to the input embedding, it should be independent of what the input was. Because we are encoding the positions, they're always going to be 0 to something or max length. There's nothing about the input that if queen is in the first position versus the third position, that should change the position understanding of the model. So that's one. The third thing is that it needs to be independent of the sequence length. So that's a big ask. So no matter how much you change the sequence length of your transformer model, obviously your weight parameters get updated, shapes change all across the model. But when you're encoding something, whatever is your position for position encoding for 0 should still be sequence length invariant. For example, if you change your sequence length from 8 to 16, your position encoding for 0 should still remain the same. So as you can imagine, it's a big ask. Like you already want it unique, but then you also want it extensible to any sequence length. And we'll get into how kind of it manages that. Again, one final requirement is that any of the numbers that are used in the positional encodings shouldn't be too large. Because if they're too large, what they're going to do is you add them to whatever input embedding there is. That value is going to become super high. And then it gets multiplied by the weight matrices. It's somewhere along the line is going to reach a softmax that is going to blow that value up even more. And then we're going to reach the same problem that we had with the sensitivity to color and shape, where some neurons are just super active and some are dead. So we do not want that, and we want like an even spread. So having too large of value would mess that up. So these are some of the requirements for a position encoding. And now I'll talk about how having the sign and the cos functions kind of helps with that. And that will be all on the board, so please pay attention.
No.
Like what were the images that on the slide before was were those represented exactly? Like how were those positional encodings working?
Sorry, who's asking the question? Oh yeah.
The slide that you were just on. No, what the requirements? Yeah.
Yeah.
Like, what's going on in those images? Like how are the positional encodings working?
Oh,
Which is right.
Oh, nothing is the right example. It's just showing the properties in numeric form. So they should be unique. So sorry, this I think the lock on the position means that it should be invariant to sequence length.
Oh, okay.
So it's just it's a picture format of the thing that I put in. That's it.
Use the word. What's white?
Oh yes, yes. So green is the input embedding. White is the positional encoding. Yeah, sorry. Thanks for clarifying that. Yeah. Anything else?
So when you push a data point to its cluster, like what do their cluster represent?
Like I said, it could represent. So maybe there is some cluster that encodes every word that has a high probability of always being the first word in the sentence. So that cluster specifically could be maybe the cluster of articles. So the, a, and. So anything that comes first in the sentence, maybe you want to push more and more towards that clusters. And that's just one cluster for position 1. There could be many such clusters. And I think you guys had seen the visualization of PCA visualization of an embedding space where similar words get clustered together. So think of it like words that occur more often in the same position get clustered more together. Mm-hmm.
Why we have the going and the one panel. Why wouldn't this and then
one reason why you wouldn't concatenate them is if you remember the quadratic growth of transformer attention matrices, if you increase the sequence length, or if you increase the embedding length, it's going to also increase the number of parameters that you need to maintain. So
Another thing is, it would just be really wasteful. If we have these really long sequences that can be on the order of like 10,000 tokens long, it would be totally a waste of memory to have, 100,000 dimensions concatenated just to like kind of show that difference. You can really get away with a much lower dimensional signal inside the latent representation itself. So basically it's just there's enough space already to just also include the information that way.
good questions.
And I'm sure you're about to go into why sine and cosine.
Yes. Okay, so yeah. So the first thing that you guys need to understand for this is what if we just use the numbers themselves? So 0, 1, 2, 3, 4, 5, 7, whatever. What if we just use all of the numbers on a number scale? And just add those. So first thing, because it's just one number.
So what you're saying is you're going to have like a component which says, I am the first, second, third, and it's just like the value, integer value along this dimension.
Yeah.
Okay, just making that clear.
Yeah. So I'm just representing the integer value in the d-dimensional, whatever, and adding that. What that is going to do is think of the numbers 0, 1, 2, 3, one hot encoded. If they're one hot encoded, all except one dimension of the encoding is going to be 1. And then when you add it to, again, the input embedding, we're going to run into the same problem where only one value is really high. Everything else does not get any information. And that value becomes larger and larger and through the network. And we don't want that. So that there's a disparity. Like I said, we want the weights to be as even as possible. For them to be as even as possible, we don't want them to be added, in such a way that only one of the values shoots really high up. Does that make sense?
You definitely need to go a bit faster.
Yeah, okay.
Should we just like give a lightning quick explanation?
Yeah, go for it.
So sine and cosine are picked because they are orthogonal. And that just means that if you were to look at the actual directions that these things were summing to them pointing, they'll be pretty, like if you were to just do a dot product of them, they'd be nearly 0. So that just means that when we actually add this representation for the component of the sequencer in, it'll be pointing in a direction that's always orthogonal to all the other positions. And that allows you to basically say that the position's independent of each other. So there shouldn't be any inherent correspondence between being the first or being the second in the sequence. They're related to the same word, but the actual directions that correspond to a difference in position are orthogonal to each other. So that's just like why we use sine and cosine. They're orthogonal.
I could skip attention and everything else completely if you want me to deep dive into the sine and cos even more, because after this, we really do need to move on to the second half of the recitation. Any particular preferences on that? Because attention was covered a lot more in detail in class. So if you do understand that, we can skip it.
Is it important to know, like, deep dive about positional encodings besides just the high level?
The way the topics were chosen a little bit was whatever maybe was not covered in class as much, and to just get you to the same level on every concept. But like I said, it's not an indication of what's in scope for the prelim or what's important and what's not.
Just for the better understanding.
Yeah. Yes, because there's variants after transformers where the positional embeddings are of different types. But otherwise, it should be okay to just understand it at a high level. Okay. Do you want to cover this part?
Let's ask if people have questions about this, or we can.
So
skip
does
through.
anybody, I guess, have any part of this interpretation of attention that they sort of get stuck on when they're either trying to compute it or, you know, work through what it means intuitively?
Can you just clarify the D term there, what that does?
Oh, yes. I can do that. So I think you had a question for this on the homework, right?
Yeah.
To understand decay a little bit, you need to understand the variance property of matrices, where
That's not, okay, wait, I'll give you the rundown. Basically, if you increase the hidden dimension, so you have the square root of dk, that's the hidden dimension of the transformer. If you increase the hidden dimension without doing the square root, the variance of the values in that in the parentheses of the softmax, that will increase a lot as you increase the hidden dimension. And that basically adds one more hyperparameter because then if you increase the hidden dimension, you might need to reduce the learning rate to counteract that. So instead of having to worry about counteracting that, you just add that square root there so that the variance is the same. And that's what question 2, I think, on homework 2 or something like that addresses that, explains it a bit more. So you can look at the solutions for that if you have further questions.
How do we determine D given a matrix? Like I'm doing the homework, but then
Given a matrix, how do you determine the hidden state? The hidden state, usually I think you have 128, 64, 256, the hidden state. I don't think that's, yeah,
it's a property of the design of the transformer.
it's a hyperparameter.
Yeah.
So we would tell you either some relation that gives you, like, specifies decay given other parameters, like the dimension of the value or the dimension of
Yeah, it's
the queries. So you'll just be given something that can let you solve for this if you would ever.
So if you're given the shapes of Q and K, which convert your input embedding to a hidden space embedding, the hidden space embedding side of the matrix is the decay.
So if the shape of the key vector is like 5 by 1, that
5 is what?
I'm just saying if the shape like the key vector is like the key matrix is 5 by 1, then does that mean DK is
If it's defined that the input
It
sound.
would be a dimension that vanishes when you do this multiplication. So you would have like.
That's a good way to put it, yeah.
If these are n by d, then the d's would end up on the inside here, and that's what gets multiplied out. That's the dimension that we're worried about here. Does that make sense? So you could have like a n by d cube and maybe a different like length of k, but ultimately that shared inner dimension that you're actually doing the sum over, the length of that dimension is dk.
So what he's trying to say is this is the dimension that gets lost after the dot product, and you're left with n by n. That's the thing that gets lost in the computation.
yeah, it's same D, right?
Yeah.
D is the dimension of those vectors that you're doing dot products with. That's what D is, the hidden dimension. So if your each of your key vectors would be D length, and your value vectors and sorry,
Key matrix is 5 by 1, then that means that 1 would be the D here.
Yeah.
right.
Yeah.
Up top.
Yeah, I know Killian had some kind of analogy in QK and VR.
Mm-hmm.
Can you explain that?
Sure. Just in one sentence, the analogy was Q is the query that's asking for what its relationship with other words in the context is. Key is the representation of each of the other words that inform this understanding. So Q and K just basically, when you do a dot product, it's just getting a similarity between one word and the other. So if cat on the mat, every word has its Q, every word has its K, and then you just do a dot product between everything, 4 by 4, and just get relationships between how similar or different they are. So QK transpose is just getting a similarity between queries and the keys. The similarities will shoot up when the similarity is really high, or be small numbers if the similarity is really low, and they can act as weights. If you see the color changes across the calculations, the some are really high. So, and then you take a weighted sum of each of the values in the dimensions of the values. So that helps again to get the weighted sum, I guess. And basically that's the interpretation. That's all. Yes, last question, because we're at the, yeah.
Yeah, suppose you're training. Right now, you're saying that the keys, but when you're training this model and you're running back propagation, there's no way to like specify that this is the query matrix, this is the key matrix, and you're running some attention on it. So what's to say that during the back propagation process, Q actually acts as the key and the
You actually can't stop that from happening. It's totally symmetric.
Okay.
We just like to talk about it that way because it was inspired from like
Databases.
yeah.
It's inspired from databases, yeah, but yeah, and that doesn't, it's just the way we make sense of it.
And is that an issue with encoder models or encoder decoder? And
I guess it's a feature.
I don't, yeah, why call it an issue? That's a bit negative, right? It's
One way I like to think about attention is that it's like a asymmetric dot product. In some way you have like words that you want to only correspond to each other, but like in an order independent way. So the more important thing is that Q and K actually just make the word do different things. So that if you were to have Q and K for like one word and another word, that would be different than if you were to swap the order of them. So yeah, that relationship works both ways, but you can kind of always think about it as like this kind of asymmetric dot product between those words, I guess.
Okay, so that was it for transformers, and now we move on to the second half. Thanks a lot, guys.
Okay, so I'll start. I'll be covering representation learning. So that's kind of just, we have this very common case where we have these very deep networks that we have all these data sets, and we're spending a lot of time compute to get these results that are kind of data set specific. And then we look back at the model architecture itself, and you can see that there's kind of these components which aren't necessarily specific to each of those data sets. You have this first part of the network, which really learns how to extract features, and then you have a classification part of the network. So the whole thing behind representation learning is kind of considering what are we actually learning when we're taking these, like this first part of the convolutional network, and is there some way that we can make useful things out of that? So almost all representation learning is kind of, if we can just ignore the specific task and not worry about classification later, what can we accomplish? So you'll very commonly see representation learning as like a bring your own classifier type of thing, where you just have this large data set, which you don't have labels for, that's the whole point. And we want to still have some way to extract useful features without knowing necessarily we're starting with. So what I'll be going over next is just what are some of the techniques that we have for getting a useful image embedder. And so I'll mainly be focusing on images here, but a lot of these techniques, of course, apply to many other modalities also. At least in the context of images, we have this very, very high dimensional vector of an image that we're projecting down to a space, and 768 is very typical for this dimension that we encode this in. So what the goal really here is there's this manifold of images, which is rather low dimensional, and we can kind of, the evidence for this is like the success of deep learning in general, but ultimately we want to find a way to help
map that manifold out. So the first thing that we can do is actually just cut off the head that classifies and keep the encoder, because in order to do a task like ImageNet, where you're given maybe 100 classes or more, you have to first learn how to decompose those images into useful things. So when you cut off this classification head and just look at what are these features that it's learned, you can see that the images as they come in get mapped to a similar place as relevant images like of the similar class. So that's like one of the important things that we want to get out of these models. And this was kind of like the first way that people started to understand these networks. So now I'll be going into the self-supervised case, because this is kind of what has led to things like GPT and the very large models that we have today, because labeled data sets are large and hard. So the first type of self-supervised learning I'll talk about is the pre-training task. So this, it was covered in class, of course. Rotation is one of the interesting ones to think about because it's such a simple idea. You're essentially just asking an image, like, was this rotated in some way? And that's a very, it seems like low dimensional signal, but in order to actually accomplish that task, you have to have quite a good understanding about what's actually inside the image. So whenever you can find a task that's very easy to label and correlates with understanding an image, that's typically grounds for like a pre-training task. And then the next thing you can focus on is contrastive learning. And so that's where you're taking your data set of some kind, and either you can take, like, if you happen to know roughly where things are classified, you could pull positive examples that way. But for the most part, we're only looking for examples that we can augment, that we like know for sure are sourced from the same input. So although these look very different, and some of these are objectively bad, actually, augmentations, I think the Sobel filtering, if you read the paper, is actually one of the worst there. But things like color also can be important. So the ways you distort those, of course, do impact how your model learns things. But these augmentations are what allow you to kind of classify these slightly different images, because as you change the color or flip something, that vector in that huge space completely moves around, but those end up being very similar to each other just because we process these images kind of as an entirety. So some of the objectives that we've seen that models can go in for learning contrastive learning are sim-clear and triplet loss. So I put some visualizations here that kind of can help you visualize what those types of loss functions actually prioritize. When we look at sim-clear loss, I guess like the way that I like to think about it is you have this kind of spiky distribution around your input that you want your positive distributions to get near to, and you're going to punish the negative examples if they're too close to that. So a lot of people, you know, they see the temperature parameter and it kind of freaks them out. But when you kind of view it as like the radius of this distribution, it kind of makes more sense. So as you increase this temperature, you're ending up, and you're making more values kind of near each other, similar to each other. And so you're being less strict about, because it's a ratio, I guess, that matters here. Like that green cosine similarity arc there versus like the orange one, those represent how proximal to this center distribution you are. And if you're assuming that X, this space of images, like things near X are like X, then as long as X is somewhat close enough, doesn't matter how far, but the ratio itself, that's really what this will start to penalize. So the probability is almost like you're sampling where on that distribution from the center is X versus, or the positive example from the negative example. And like the densities of those kind of help you with the actual probability that one would be picked over the other as positive or negative. Triplet is also put down here. It's kind of like you establish this quadratic form around your image, and you're saying that everything that is in this class should fall near it, and negative examples should just be outside this range period. So that's kind of what this, like this little divot in space should be reserved for this class only, is kind of the idea. This tends to be a very finicky loss function. So the hard introduction of a loss once you end up inside this like parabola means that it's not very robust to having like different sizes of these distributions and things like that. So there tends to be a lot more playing around with triplet loss and instabilities due to the fact that I'll keep going. This is too nitpicky. So now I'll go into multimodal. So it's still kind of under contrastive learning, at least the way that Cliff represented. So we're taking images, instead of images to images, we're doing images and the captions that appeared with those images. And we're kind of making the assumption that people tend to write things that correlate with the image themselves. And so the goal is to, when you compute these similarities, to make that diagonal as large as possible and minimize every other value. Because that means that there's a pretty one-to-one correspondence between caption and image that we're assumed to hold. And pretty simple. Are there any questions so far? Because I haven't really been paying attention. All right, let's keep going. So Clip likes to make this really useful space where images and text live kind of in harmony. So the utility that you can get out of this is that images and text can now be compared as if they were of the same distribution to begin with. So a lot of the applications you can see of Clip they can span anywhere from like searching images with text or clustering images based on their captions, things like this. There's many useful applications of Clip, and they're all based on that contrastive objective of making sure that diagonal is maximized. Do any of you know what architecture I'm hinting at here? So this is a cropped part of a larger image. Do any of you remember what objective this corresponds to? Does somebody raise their hand? Yeah. Yes, it is Dino. So do any of you know already what this is? How about now? All right, one more. Pretty clear, right? So somehow all of you at this point have decided the content of this entire image. And so of course, this is the space shuttle. And that's the whole objective of Dino, is from this small image, you're able to infer the context around it. And that means you have a very good encoding of this image. So this is the architecture behind Dino, or at least how you would train something with the Dino objective. You're taking this global view and a local view. The local view is more constrained and doesn't give you all the information. So what you're trying to do is this student, which only has a limited view of the entire feature, has to emulate the teacher, which has access to all of its knowledge. I will quickly go through the actual, what I mean by like the hot and the frozen weights here. So although we do update the teacher, we don't have it in advance. Like when we start to train with Dino, we don't have this. So what we do is we randomly initialize the networks, and then the student still has to match kind of like random output of the teacher. But to do that, that would, like, the way that the teacher would make its random prediction does depend on the entire image. So this is almost a form of bootstrapping, if you are familiar with that. There's some other models that do this too. But as the student starts to emulate the teacher better, we use this moving average of the student to the teacher. And together they start to interpret what these images correspond to. So does everybody like this so far? Are we comfortable with how this training works?
Wait, are we randomly initializing the teacher?
Yeah, both of these models, we don't have them to start. So we don't have, I guess you could start with an encoder, but we're kind of starting without one. So yeah, you would randomly initialize both. And then no gradient goes through the teacher, but we do update it outside of gradients.
That's what the self-supervised means. You don't have labels or any information yet about the self.
Yeah. So I'll kind of talk about okay, we're doing vision transformers now. So there's really not, oh, sorry, you have a question.
Yeah, I don't really get the part of, I mean, is it sort of like an industrial thing? Like, are we sort of like, you know, the student gets trained and then he compares with the teacher, which has a global view, and then goes back? Or like, how does it work exactly?
So I guess let's think of something very specific. So like, let's think of animals. the student is going to make more frequent updates than the teacher, or at least more rapid updates than the teacher. And so the student will see like pictures of maybe like the legs and hands of like a goat, or like maybe the side of its face, whereas the teacher can see the whole thing. And gradually the student will start to make predictions that correspond to that entire image, rather than just like the core feature it sees, because it might only see like the horns, but after enough iterations, like it's trying to emulate what the teacher sees. So the teacher sees everything, like with the horns and the whole body. So when it sees horns, it starts to predict more towards the whole body too. And then I guess it's hard to explain why bootstrapping works. It seems kind of miraculous, but when you slow it down, they're both kind of doing the same task of understanding the image, and there are ways this collapses, and that's why centering is necessary. You don't need to understand that in a very high level. Have I answered?
So in both cases, are we trying to predict, like, is it like a classification task? Are we just trying to predict what the object is?
Yeah, there's no labels here, so we can't predict what the object is. Actually, the whole goal here is to just, given a small part of the image, you have to kind of make like a pseudo class that corresponds to what you think that will be. So when you see the engine of a rocket, you should kind of be trying to map that to a rocket. That's the objective we're seeing.
So we're trying to minimize the distance between the roles and the goal.
Yeah, we're trying to make sure that, yeah, so this is cross entropy here. So we're just trying to say that the embedding that the teacher produces and the student produces need to be as similar as possible.
So why are we doing the update on the, like you said, it's like bootstrapping, right?
Yeah.
So that means like even with the teacher case, it's sort of like updates after 3 steps, right?
Yeah, they use an exponentially moving average, so I think this happens more frequently, but it's like a very small update. Yeah.
But what are we trying to update? Like, what are we trying to learn with the teacher? The student is what we're trying to get.
So the teacher learns from the student as well, because it keeps getting its weights updated from the student. Like the student learns something from the teacher, right? Because it's trying to get the same output as the teacher, which has a global view. And then the teacher has this EMA, exponential moving average, of the student's weights. So the teacher is also learning from the student in a sense. And in the end, you have both of the student and the teacher kind of converging in what they define these classes to be. And they learn, so we don't know what they end up learning, or we don't decide that before training the model, but they end up converging on some representation that makes sense to both of them. Does that make sense?
Teachers are random, so the way that it understands images is also random. And because the student and the teacher are both trying to understand images, I guess one way, like one source of a model would be to look at what the student's understanding. Yeah. You had a question up there. Are you still?
We probably need to get through this a bit faster.
Okay.
Oh, well, more questions.
Which one do you keep at the end, the teacher or the student?
They should really be, I guess, the same almost.
I think the teacher,
keep the student, I'm pretty sure.
I might be misremembering, but the teacher has this bagging concept as well, right? So you've averaged a bunch of models, so the teacher sometimes can, I think, perform better as well. So it's an interesting question, though.
Actually, I haven't thought of that.
Yeah.
Yeah, but I think it's either would work, but the student would be the one that tries to predict the larger context. Sorry. So roughly, I'll say, to make this quick, you could have some adversarial thing that happens here where the teacher actually just starts to predict based on the region the student is predicting. So they end up with perfect agreement. Centering forces the teacher to also pay attention to the whole image, I guess. But I can't really explain why that happens. It makes sure that the teacher can't overfit to the student's view.
Like what happens if you just decide that everything's the same class for everything, right? There's nothing stopping that. The centering is one of the steps that stops that. It also has if you remember the softmax with temperature, it also has that as part of the centering. But it's,
it's a really hard to understand.
It's not that easy. Yeah.
It just prevents it from collapsing. You don't need to understand it very much. Okay, I'll try to keep going.
We'll answer your question at the end. Sorry.
I'm gonna skip this for now. If we have time, we can come back to it more. There's really no difference other than you're using small patches as tokens. We'll cover this later too. Basically, you can think of SWIN as a middle ground between deep convolutional networks and fully like vision transformers. But we'll cover that if we can later. Oh, goodness. I'll get through this really quick too. Dino, when you look at the actual pieces that come out of those small patches, if you perform PPA on them, you get these representations here. They're really good. They seem to correspond very strongly with semantically coherent concepts. So if you were to compare like the flying things here, like you kind of have the head of the bird and the head of the plane, ending up with very similar representation. It's able to do that. Just to get to the point, theoretically, because you can train CNNs just fine with Dino, like you can do the same task. The authors did, and they had success there too. The main problem and the reason why we like VITs for these very specific pixel level tasks is because they have immediate global receptive fields versus CNNs. So the features at the very end of the CNN depend in a very long, convoluted way, literally, from the pixels that started with them. And so when you try to figure out what pixels corresponded to what, you end up with these very blurry interpretations. Whereas vision transformers themselves, you can just see into those attention results from those patches and get really good results. Yeah. All right. Okay.
Quickly, I think, does anyone have any general questions about CNN stuff? I think like you guys did a lot of practice with CNN, so.
There's one at the back.
Oh, yeah. Oh, I'm covering that. Okay, but just like this stuff of like the figuring out the dimensions of like, okay, what is stride, what is padding, like any of that stuff. That's like pretty basic. So I think you have to be able to know how to like make this function, but we're not gonna, I think that's like basically it. Okay. This question, I think a few people had questions about this, so I think, should I give you time to like answer it? Should I just go over the answer? Okay, yeah, let's just go over the solution. Okay, so the solution, each layer, I mean, it's pretty straightforward. You have like the 5x5, and then because the input channels and then the output channels, you have to have one filter per input, and then each one of those has like an output of the number of channels it has. So that's why it's like 300, and then you have 4 of these 1x1s, and then 2 of the 3x3s, and then the total is 404. It's like straightforward, right?
The question at the back.
Yeah. No, the residual connection does not increase the number of parameters. Okay, well, you could do like some form of like linear projection, but normally no, because you're just adding like you're adding like this input to what's going on here. So you don't actually have to have like any learned parameters. Any other questions? Okay, cool. On to the next topic. Okay, this is the filter one. This is actually different from the prelim question, but it's like the same concept. So these are the set of filters, and then this is the input image, and then it'll be time to like match up which one goes where. And also there's this like link where you can like experiment with them and like, yes. Mm.
Itself is higher dimension than what is that right?
It would only be a higher dimension if you're like concatenating it. If you're just simply adding it, oh, you mean like the dimension here versus here?
Yeah.
That is true. I'm not sure.
You just have to fix some downsampling. It could be max.
Yeah. That's a good point. I think that usually if they have a mismatch, you would have to have like some other thing to like project it into the same dimension. But in this case, you can just like assume that that did not happen. It's just adding.
I think you guys have this on.
This is on the practice panel.
Project or work, but maybe one of the slides that Jennifer covered, but adding the 1x1 convolution helps match up the dimensions that get added. So maybe try to look at that slide. 1x1 convolution explanation. Yeah.
Sorry, quickly if we could.
What's the difference between concatenation and adding, like in res nets versus dense nets?
Concatenation would be like joining the like matrices, like putting them like side by side, versus adding would just be like element by element adding. Yeah, okay. Back to this. Can anyone like tell me like what's going on in each image or tell me what each of the filters is doing?
Do people find this confusing, how to visualize this, think about this? I see some nods.
We can start by describing what's going on in each image. So what is going on in this image? It's not very clear, which is my bad, but it's supposed to be like making the image sharper. Which one of these filters makes an image sharper?
Think of it this way, the way an image would become sharper is every pixel gets brighter and everything around it gets darker. So that's how we try to find the correct one.
There's two.
So for understanding it, if you imagine the values as like luminosities here, this will look like what it'll be activated by. So.
Okay, actually, I think that the confusion is between this one and this one, right? So can people first tell me like which one this filter matches up with? Yes, in the back. The bottom left. And why is that the case? Yeah, yeah. So it's going from like whatever is from like in the, I guess, yeah, Y direction or from right to left. And this one is more like highlighting the horizontal lines, right, in the image. So this filter would be like this, but if you rotated it. What about between these two? Which one is which? I'll give you a hint. You should think about the sum of what the filters are. Because this filter sums to 1 and this one sums to 0. Yes. Yeah. Why is that the case? Let's do for both of them. Yes.
Because of what you just said about the sum of the values.
Yeah.
So because the sum is it's 5 minus like the sum of the outside you do 4, then the pixels would have like a brighter value. So like not all of it being dark like in the second image.
Yeah, yeah, exactly. Yeah. The image on the left is a lot brighter. So it means that between these two filters, it's the one that has like the higher sum. Okay. Yes.
What would happen if you had like the negative column on like the left side and the positive column on the right side for like the vertical line?
It would look basically the same.
So here you can see that the white, if you look at if you look over here, you can see that it's lighter over here and kind of darker over here. Even though over there it's symmetric. The reason is because over here it's on the right it's negative, right? So on the right, if you have something that is dark, it's gonna make the center, it's gonna make stuff lighter. Does that make sense? So you have something that's dark, these negatives multiply with something that's small, so it's gonna make it lighter. And so if you flipped it around, you have white portions over here and darker portions over here.
Yeah, it would basically be like flipped on the x-direction. Okay. Yes. What do you mean? This is like as a convolution filter.
Must be applied to each pixel or like some kind of object.
Oh, this would be on the pixel level. Yeah.
These would be 3 by 3 regions.
3 by 2.
Yeah.
So you'd be applying each filter to 9.
Let's move on. Okay, okay, moving on. That's just the name. Okay. Okay, I think the rest of the content of this review is going to be covering like image generation. So we're gonna do GANs, VAEs, and then diffusion. So starting with, yeah, I think, okay, I'll go quickly over GANs. So what is the motivation for GANs? Essentially, the reason why they were first created is for like conditional image generation. So instead of like VAEs and like diffusion, which is, I guess like diffusion is specifically like sampling from a Gaussian distribution, whereas GANs was originally created like if you have some image and you want to do like style translation or like something like that. And originally, like a long time ago, people just use like paired samples, but the problem with that is that there's not enough data because usually like image data sets are just like individual labels and it's very hard to form pairs. So the example that they talked about in class was like translating horses into zebras. So, okay, so essentially you have an adversarial training is like a very broad just type of learning, and it's very similar to like the teacher-student learning, but I think it's like the opposite. So instead of like the teacher and the student trying to help each other, you have one model that learns by competing with another model. So it's more of like a zero-sum game. And so you have the generator, which actually performs the image translation or like produces the image, and you have the discriminator, which tries to predict whether the image is fake, like generated, or if it's from the data set. It's like it's a gold image. So the discriminator essentially tries to measure how good the generator did. So when you train them, you first, I mean, you can do it in either way, but you usually like randomize each model and then you update the discriminator and then you separately update the generator, but you always update the generator using the feedback from the new discriminator. But can anyone say like why you can't train them simultaneously? That's a tricky question. Okay. Yes.
They overfit to the image that they're working on at the same time.
No, because you can still train them in batches. But I mean, I guess that's on the right track. So I'll say like, I will accept it. Okay. Yeah, you could say that. I think it's also, I mean, adversarial networks, like GANs are just generally really hard to train because you have like these two models that you have to fit at the same time. But usually, yes, if the discriminator is doing too well, then it's very hard to train a generator. But if it's also doing too badly, or if the discriminator is training at the beginning, then the generator it's like trying to train for like a moving target. That's going to be very difficult. So that's why I usually have to do them separately. Okay, this is a loss. I mean, I think we covered like binary cross entropy a little bit earlier. So this loss is just based off of binary cross entropy, or just like if you think of like generally negative like log probability. So we have the real sample, which you think of as like as a positive sample, and then we have the negative sample, which is like generated from X, but then X is like translated. Or I guess you have a Z, which is like the not the correct category, and then you generate an image from that. So usually they call this like Z prime or Z hat. And then that is the negative sample. So the discriminator is just doing normal binary cross entropy. However, the generator, the loss is the same thing as the discriminator loss, except you just negate it. Because it's trying to like it has the opposite goal. Okay. Additionally, GANs can be used for unconditional image generation. So this is like the idea that VAUs and diffusion uses, which you sample from like a Gaussian distribution and then use that to generate a new image, which you don't have to have like a previous conditional image to generate using. And usually GANs, they generate high quality images, but their problem is that they're not necessarily trained on generating like images using the true distribution. It only generates what it has learned fools the discriminator the best. So this is called like mode collapse. So for example, like if this is the true distribution that you of the image class, you might only get like one smart part of it because that's what it has learned works the best in the objective. Any questions about GANs? Okay, cool. Yeah, I mean, we're gonna go through this question for like all of these models. So first, can we look at GANs? Is it trained using a likelihood-based objective? Who thinks yes? Okay, who thinks no? Okay, Anyone want to answer why it's no? Okay. Yes.
It's not a likelihood, it's either like a yes or no.
Right. It also doesn't generate, well, we say it's not generated from a likelihood-based objective because, like I said, it's not generating based off of the actual true distribution of the images, right? Whereas VAEs and diffusion actually do. Oh, okay, sorry. Oh, that's true. Okay. Okay, has a learnable encoder that maps the data to a Gaussian distribution. What is the answer to this? Does anyone think yes? Okay. Does anyone think no? No one's raising their hand. Yes. Okay. Why is it no? Yes. Right. Okay. What about latent variable? I mean, these are all no. Okay, I think no one like that one's obviously okay. That one's obviously no. Okay, learn to generate images by fooling discriminator. Obviously, yes. Generates high quality realistic images. Yes, because I just said that. Generates an image of a single forward pass of the network. That's a yes. Anyone confused? Okay. Often suffers from poor diversity. Yes. And transform samples from unit normal distribution to samples from the data distribution. This one is also yes. Okay. That's what I said. Any questions? Because we're running out of time. Yeah. Right, so this is going back to this where you can input like noise and it should generate you something. Okay, the idea is that, so for here, right, you're giving it like a picture of a horse and then it generates an image of a zebra based off the picture of the horse. However, they thought, okay, well, we have this generator that can take an input and generate a picture of a zebra. What happens if we just like feed it like bullshit? Like it's still going to generate a picture of a zebra. So that's why you get like, you can just do like a random noise sample and it should give you some picture of a zebra that's not conditioned on anything. That makes sense.
To do the zebra, is it like you tell it?
Well, the model has been, the objective that it's been trained on is to generate a convincing enough picture of a zebra to be able to fool the discriminator. So if the model is robustly enough trained, it should be able to do this task.
Without you telling.
Yeah.
So if the discriminator can tell the difference between a zebra and garbage, which is easy, right? Then you're not gonna be able to fool the discriminator. So the signal would be to learn to fool the discriminator. So you eventually will produce a zebra. Yeah.
So we're being to generate images of a certain class that we train it, right?
Yeah.
And then when we run it, you should just expect it to produce one of those things.
Yeah. Well, the idea is also that like, okay, this picture of a horse, when you look at it, you see a horse, but it's also technically it does belong within some normal or like Gaussian distribution, right? So it has some probability of occurring, but the model doesn't know the probability that it occurs in. That's why we don't say that it's modeled, like it's not trained using a likelihood-based objective, but it's still able to take like some data and then generate a picture of a horse, like of a zebra from it.
Okay.
Okay. Move on.
Okay.
I think it'll make more sense when we talk about BAs.
Let's go this.
Yes.
Okay. Do you guys remember how units work? Yes, most of you do. Okay, so I'll go through this really quickly then. So unit, it has two parts. You have this encoder part and the decoder part. The encoder part kind of gets the high level information, it distills it, and the decoder part has kind of then gets it back to the original size of the input. But the skip connections are kind of the secret sauce that give you have the high level information that's been distilled, and the skip connections give you the low level fine grained details that you lost while distilling the high level information. It allows you to regenerate something that is still has the high level information and the low level information. Okay, so VAEs. Do you guys feel comfortable with this? Any thumbs up, thumbs down? Want to get an idea? I see some thumbs down, some thumbs. Okay, some just see a distribution of them. Okay, so data manifold. I think Sean touched on this a little bit, but we have, for example, in the case of images, if you think about images of dogs, right? The actual number of if you think about the actual space in which dogs exist, if you had a 64 by 64 by 3 image, you can't just sample any image from the space of 64 by 64 by 3 images and get a dog, right? The probability of you doing that is super, super low. And the reason is that most of these distributions lie on a very low dimensional manifold. Manifold is a fancy word for, let's just think of it as a space, low dimensional space, nonlinear space. And so naive random sampling in the space won't generate a photo of a dog, right? And if you want to be able to generate photos of dogs or photos of something, we need to find a good way of being able to sample on that manifold. And GANs just directly go to it. VAEs do have this two-way path between the manifold and noise. So I'm going to first do a very brief overview of VAEs. So you have autoencoders. They take in an image, they get your latent variable, and they decode it. And we typically use mean square error or mean absolute error to compute the reconstruction loss. But this doesn't have any generative. This doesn't have the generative element of that we want in VAEs. So one question you can ask is: so you want to be able to generate images? How can we sample from this latent space? Do you guys think that we could can we sample a Gaussian, a 3-dimensional Gaussian in this case, and maybe likely get a reasonable output? What do you guys think? Crickets? Anybody? Yeah. Exactly. So there's some distribution that's being mapped to, but we don't know what the distribution is, right, beforehand. So the very simple way to think about VAEs, it's not exactly completely accurate, but simple way to think about it is let's add regularization to encourage the latent space to approximate some prior. Usually you use a Gaussian. And this kind of gives you what you end up with elbow, right? You have a reconstruction term. So I want to be able to make stuff that looks reasonable, which is just the same stuff as just vanilla autoencoders. And we also want to be able to sample from the distribution. So hopefully this term makes sense because the KL divergence is going to make these two distributions be the same. But I'll go over this in a bit more detail in the coming slides. So first, as you probably remember from lecture, we try and make a distribution. So we use a probabilistic encoder. So what we do is we predict a mean and the log of the variance. And if you guys remember, why do we use the reparameterization trick? Do you guys remember why? Anybody know why we do this? Yeah, answer with that. Yeah. Yeah, you can't really backpropagate through the sampling process. So the idea is that, okay, we don't have to worry about backpropagating through sampling from a standard Gaussian, but let's backpropagate through the mean and the standard deviation that gets predicted. So what you end up with is this term, and this is the reconstruction term. And do all of you understand what this means? Because some people in office don't really understand what this meant. What does the subscript mean? Can somebody who knows or thinks they know answer? Do people thumbs up, thumbs down if you don't know? Okay, I see a lot of thumbs up. Okay, I'm just gonna give the answer. So you see this. What you're doing is and sometimes you actually don't even see this but essentially what it's saying is that I have my encoder. It's going to give me a distribution once I pass X in, right? Is everybody with me? So now what I'm doing is I'm going to sample some Z from this distribution, some latent variable. And over here, what I'm doing is I'm saying, okay, given that I sampled something from the distribution that I've predicted, what's the probability that I get back? What's the likelihood of getting back the X that I originally encoded? Does that make sense, everybody? Or is anybody still confused about that? I saw a lot of thumbs down this region, so if you guys have any questions about this, please ask now because this is really important to know for the entire alpha derivation. Yeah.
Wait, so like Z's level
Mhm.
that's like the distribution over Z's, like in your input image,
Mhm.
and then inside the log, like data X, the likelihood of getting back the original.
Exactly. Yeah.
The
Exactly.
likelihood of getting the original image over like the distribution of like latent space.
Exactly.
joins.
Yeah, that's right. Any other questions?
I have a question.
Yeah.
I have a question on the encoder. So does the encoder just spit out the mean and variance and that's it, give it an input image?
Yeah. Yeah, but actually log variance, but yeah. Yeah.
We're like calculating this expectation like in practice, like
Mhm.
it's like all conditioned on like a single X. Like
Yes, but for
you're like given an X and then you can calculate this expectation.
yes, since expectation is something you can approximate using Monte Carlo sampling. That's what you end up doing for. Oh, do you guys know what that is? You just sample a bunch of latent variables, right? And then you average the output answer. That's what that'll approximate the expectation. Am I answering your question?
Given like in
Yeah, given an X. So here,
Okay,
in training, you use the training data. So you have a bunch of images, right?
Yeah.
A bunch of something, so you can compute the distance.
So would you say like that's like a loss for like a single like training sample? Like
Yes,
averaging
exactly.
six
Yeah,
marks?
yeah. This is a reconstruction loss. I should have added some label maybe. This is a reconstruction loss. I saw a question somewhere else. Someone, yeah, sorry.
Can you explain one more time how it is, guys?
So this, is there a particular about using about, so it's drawn from a normal distribution that mu and this and log sigma squared is predicted by the encoder. So the encoder gets X and then it predicts log sigma squared, log variance, and it predicts the mean of this Gaussian distribution. And then what I'm going to do is I'm going to sample from it my latent variable. So it's predicting a distribution over latent variable. Does that make sense? Any questions?
Think of it like the reverse of normalization. In normalization, you would subtract the mean, divide by the standard deviation. Here, you have the normal distribution, multiply it by standard deviation to scale up instead of scaling down, and add the mean. So we shift it instead of negative.
Why do you apply diagonal and
So this just takes the value and makes it an identity matrix with not a zero matrix, but with the diagonals having the it's like numpy matrix. You can think of it like that. So this is a vector. Now I'm going to take that vector and make it the diagonal of the matrix, and the rest the off diagonal elements would be zeros. That's all it is. So this makes it a vector, a random vector that is drawing from the distribution. So that isn't just a scalar; it's a random vector. Okay, see more questions the more I explain stuff. So I must be doing something really wrong.
No, really right.
Yeah.
Really right.
Really, okay, yeah, really right. Yeah, go on.
go through one more time how this makes it like differentiable or like you can back propagate?
Oh, okay, so why do you parameterization trick first? Here you're predicting a mean and a standard deviation, right? So once I draw some noise, I can be like, hey, I'm going to treat the noise as a constant basically with respect to all the parameters. Because the noise that I'm drawing the noise is drawing from this standard Gaussian over here, that is not affected by the parameters I have in my neural network. So now I'm going to draw some noise, and then I'm going to be like, hey, so how do my sigma and my mu actually get affected? How did in this case, it would be affected by sigma. If I have a really high sigma that's going to make a really massive variance, how does this affect my loss, right? And if my sigma is really high, then I might be like, okay, it's too high, I need to reduce it. Because when I draw random small amounts of noise from the standard Gaussian, it leads to bad distribution. Does that kind of make sense? So if you were to just hide all of the sampling process if you were to hide all of this mu plus sigma times noise in one sampling process, there's no backpropagation you can do, because then you just here you can at least backpropagate through mu and sigma, but if you hide that all in a bigger sampling process, you can't see what the mu and the sigma are. Does that make sense?
Yeah.
So you're basically
But
unpacking.
doesn't it give you mu and sigma?
Well, that's exactly why we are predicting. Like you could just predict a distribution, right? And then sample from it.
So imagine,
So the
so-
whole parameterization is like you taking.
Yeah, and you do get the mean and the sigma, but the thing is that you don't know. Okay, let's say that I asked you to backprop to sample from a standard Gaussian with mean 0 and variance 100. Now if you sample something, I don't know how my variance 100 affected it exactly, right? Because maybe variance 10 would reflect the same thing. It's just that it's more unlikely, but it might reflect the same thing, right? But now let's say that, hey, I'm gonna have variance 100, sample from a standard Gaussian, you get 0.9, right? Or let's say you get 2, right? And then I get 200 as my, or 20 as my value, that maybe 2 times 0.2 times, or 2 times 10, that's standard deviation, I get 20. I can be like, hey, that's actually really unlikely given, that's unlikely to actually happen given my noise that I sampled, because usually you don't sample 2 standard deviations away from the standard. Does that make sense? Or I'll explain it afterwards.
I'll try quick. You can imagine that before the forward pass, you've decided what the noise is. So it's literally constant. You can just see this as being a literal normal network, like with nothing weird happening. It's just that before the forward pass, we keep changing that value.
The noise that you draw.
Yeah, sorry.
I'll explain it afterwards if it's so confusing. Sorry, but it's not clear. Okay, I'm going to move on to the next slide. Okay, so if you do the math, this actually turns out to be, if you can follow the math in the slide, it's not too complicated. This ends up being mean squared loss. So it's pretty easy to compute. That's basically the upshot of this slide. Is there anything specific about this slide that's, the math isn't too complicated, you can see that this distribution is defined to be the exponential, and the exponential and the log variance cancel out. And it's not too interesting either, in my opinion. I'm going to move on to the
Just ask
sample.
Claude or some other language model if you have trouble.
Or ask on Ed. We also are paid to answer your questions. Okay, so sampling. So although we are now forcing it to be a Gaussian, it's possible that we have multiple different Gaussians that we're drawing from. So in the end, this case, right? What happens if 2 is in some Gaussian over here, right? That's where we draw the latent variables that the number 2 corresponds to, and 5 is over here, right? Which, how do we want to be able to sample from a Gaussian, just one Gaussian, and still be able to get all of these different numbers. We want to be able to get variety, even though these distributions, each of these individual items might correspond to a different distribution. Am I making sense, by the way? I feel like I'm losing some of you guys. No, am I not making sense? Actually, no. Okay, I'll try and explain this one. So back here we have that it's predicting a mean and a standard deviation for each item, right? But each item could have a different mean and a different standard deviation, right? So if you have a different mean and a different standard deviation for each input data, piece of input, each image in your data set, how do I draw from that latent distribution and still create, if I have one, let's say centered at 100, I have another distribution centered at a negative 100. You know, if I'm sampling from 100, then I'm never, with a Gaussian centered at 100, I'm never going to get the element that has a latent distribution centered at negative 100. Does that make sense? Any questions about this? Am I going too far? Okay, I think some people get it. I'm going to move on. If you guys have questions, please ask me afterwards. So the trick to allow us to just sample from one Gaussian distribution is that we then add this prior matching term, the scale divergence, and we're going to say that, okay, all of these distributions, we want this distribution, the encoded distribution, to be close to the standard Gaussian. So that way I can't have, or it's very unlikely that I have, or you could penalize for having a Gaussian centered at 100, or a Gaussian centered at negative 100. So this allows me to move all of these distributions that are once all over the place into one place, so that I can just sample from here. And then I can still get diversity in what I'm sampling. Make sense? Any questions? Yeah.
Is P of C the Gaussian?
Yes, that's right. It's the product. Yeah, it's a Gaussian. Yeah.
What is the notation between P of C and Q?
It's double bar over here? I think it's just stylistic. I'm not exactly sure why they put the double bar.
Yeah, there isn't, I mean, it's this, I think one reason is that this is often kind of used as like a distance, but this is actually not symmetric. So if you were to switch those terms, it would be a different value. So I think that might just be there to indicate that this isn't symmetric, even though it's like a distance.
Yeah, okay. You had a question.
Yeah, now there's like overlap between different classes, so what if like different classes get mapped to the same place?
Yeah, that is kind of what you want. So you want different classes, all the different classes to be in the same latent space, so that you can just drop standard Gaussian and you're gonna get one of the.
What if it's the same exact vector?
The same exact. So the VE then will choose something that is reasonable
Can I
because.
hop in?
Pardon?
Can I hop in?
Yeah, sure. Go ahead.
Did we go over MNIST and VAs in class?
Yeah, they did.
So if you think of the numbers like 3 and 8, those can kind of morph into each other in a way, right? So VAEs will try to configure space in a way that those classes all cover and fit together, and the transitions are hopefully meaningful.
So it's a continuous transition almost. So there is a slide, I think, in lectures where they show a almost mesmerizing image of all the different numbers kind of transitioning from one to the other. I didn't include it, but yeah, so you do end up, you want to share the space, and it allows you to sample from one Gaussian, one distribution, and so you get diversity. There is a continuous progression.
Technically, the same could be said about word embeddings that go from a higher dimension to a smaller dimension. There could be stuff that. But it doesn't. It's represented.
Okay, will you guys have an issue if we have diffusion end at like 9:10? Okay, so I don't hear a no, so, okay. Do people have questions about this? Do people understand elbow? Because it's pretty important that you understand. I mean, it wasn't the previous prelim, so I guess that I haven't seen the exam, so I don't know, but I guess that this is something you should know. Do any of you guys have any questions about elbow? I'm not going to go through every step, obviously, unless you guys have questions about a particular step. No, okay, I see one more.
Why is it useful?
Why is it okay? I guess that is the question of the homework, isn't it? Is the homework? Okay. Yeah, I'll get to that in a second. Any other questions about the steps on the derivation? Okay, so I guess the main thing that I remember that we have these two parts in the derivation. One gets you to this, and then the second part allows you to split it up in reconstruction and power matching. But just note that you get two KL divergences in the derivation. One pops it over here, and then you say that this is always going to be positive, and you can ignore it, or you can. It allows you to make a lower bound. And the second one, second KL divergence pops it over here. So why is it useful? So I guess maybe this like sort of helps to answer. So actually computing this P of X is really complicated because you have to go through every single latent variable, right? You have to do an integral over it, and that's intractable because imagine the latent space is continuous. It's no easy way to really do that. This elbow, though, once you get to the end, you see these two things that are very easy to compute. This is just two Gaussians, mean square error, easy, right? And this Monte Carlo sampling. So you sample it, put it through it. You sample from this distribution, which is the Gaussian, right? Easy to sample from. You sample from this distribution, and then you calculate this log probability, and then you put it back, and then you keep doing that and average your resulting answer. That will give you an estimate of an unbiased estimate of the expectation. And you can see this distribution down here. So as you increase the lower bounds, as you increase this is the lower bound of here, right? So yeah, any questions? Yeah.
I have a question more about not about elbows,
but
more about Q versus Q.
Mhm.
So Q is latent space, right?
Q it encodes into latent space. Q itself is in latent space, though.
Okay.
Yes, that's right.
So that latent space captures as much of actual space as possible. So if that's the case, I understand that Z is lower dimensional. Well, why is it that integrating over Z is still attractive? Because isn't it still Gaussian?
I don't think integrating over Gaussians is easy.
Well,
Yeah, I don't think integrating over Gaussians is easy. It is a Gaussian though. That is right, but I don't think integrating over Gaussians is easy.
but he's asking about the expectation over Q, two lanes, not.
Wait, sorry, what's your question exactly?
Yeah, I guess like, so you can't integrate, right? Why is it that you can integrate over this? Is it just?
You're not integrating over this. You're sampling from it. So you sample from the distribution, and then you keep sampling a bunch of times, and you can imagine as you keep sampling, you get some representative idea of what a Z vector could look like, and then you just plug it into that to see what the probability would be. Yeah. P of X is the probability of the data, so it's what you start off with at the very top. Does that answer your question?
I mean, I guess.
Okay. Yeah. Okay. So drawbacks. So images can be blurry. Can people tell me why Ganson has this problem? I put that on an exam. I was writing one, but I'm not, and I haven't looked at the exam. Yeah, that's really easy to discriminate the tell us that. So can people tell me why these make it blurry? Is there does anybody have intuition? Yeah, go ahead.
Isn't it that they're like producing like most likely images
Mhm.
and like actual real things are not likely by like the mathematical term?
Yep. Yep, exactly. So since you're trying to interpolate between, you're trying to minimize this error that is between different distributions. And the way you do that is you end up, if there are different possibilities, instead of just sticking to one, you just hedge your bets. And you're like, okay, I'll have a bit of this possibility, a bit of that possibility, and it ends up being blurry. So yeah, that's the main reason. I like your answer though. Okay, so this is a summary. So you have these, you're mapping from the standard normal, from a Gaussian to the image manifold. And by the way, with generation, you just use the decoder. You sample from the Gaussian and you chuck it into the decoder, and you can generate an image, right? Just want to make that clear if that wasn't clear. The elbows are lower bound. So by maximizing that, you know that you're maximizing log P of X as well. Or you're probably you're getting closer to maximizing it. Or you're making its worst case scenario better, I guess, is a more complete way of saying it. Any questions about VAEs before I hand it over to I have some practice problems as well. Yeah.
What is the actual architecture of VAEs?
Yeah. You can use different architectures, but unit is one that we'll say that for this class. Unit is one of them. Okay. So questions. Okay, so I'm gonna go through this a bit faster than than what we did before. Huh? Yeah, sure. Okay, we'll first do this then. Wait, hold on.
Maybe we should use.
Okay, yeah. Did anybody have trouble with the homework problem? Do you guys want to go over it, or should we skip it? You guys want to go to sleep earlier? Skip? Say skip. Okay, fine, you're gonna skip. Let's skip this as well. And yeah, let's skip this as well. Whatever. Okay, yeah, diffusion.
We open slides.
Just disconnect that because it sends. Oh, you need to reload it. Okay.
Like your lightning round. I guess so now we're gonna go over diffusion models. That's the actual generative models, right? That everyone knows about. You've covered it really recently, so I'll probably try to go a bit faster over some things. But the main idea is essentially try to denoise an image. That's essentially it. The high level idea is you have two directions, you have a forward and a reverse pass. The forward pass is saying you will take a real image from some real data distribution. I'll add noise to it so that it gets as close as possible to a Gaussian distribution of noise. That's the forward process. The backwards or the reverse process is just saying, okay, given noise, can I revert back my original image that would be sampled from a data distribution? I like this image usually. The way you can think about it is, I have some data distribution of our images, which is some image manifold. Might have multiple nodes, different shapes, dogs, cats. And then what I'm saying is, with my forward process, I'm taking this distribution, I'm just trying to destroy it into a normal distribution. That's just the forward process described in SDB. I can reverse it, which is what the reverse process, to an OD, which is just saying I'll take samples from a normal distribution and I'll try to guide them towards back to my input. And that's all we want to do with our diffusion model. So how do we do it? The main point is we define a mapping between a source distribution, which is like cats, dogs, whatever, and a Gaussian distribution. That's our forward process. And then we try to learn the backwards process. So we can kind of control one way, one direction, right? We take the distribution, we have the data, we sample it from like the world, and we destroy them. That's our forward defined mapping. And then we try to learn the backwards process. That's what we actually try to learn. That's like the cool part. So the forward process is just saying our noised image at time step t is just going to be the noised image at time step t minus 1 given the image at this not noise, and we just define it by adding some Gaussian noise. This creates like a Markov chain, if you remember. And given the Markov property is just like what I wrote down there, meaning that the next prediction only depends on the previous part. So the forward process again is saying what we can do, if you remember, you can reparameterize this to say that I can sample an image noised by amount t or a time t schedule from a not denoised image, not from the previous one, but from the completely clear image, but just like some reparameterization and defining this alpha t bar. And usually we can afford larger update steps further along the noising step. And you can think about it as like when my distribution is closer to normal, it doesn't really matter how much normal noise I add. I'm just going to converge to the normal noise. And what we want is that at the nth time step, our noised image is essentially sampled from the normal distribution. And as I make t large enough, that's essentially going to happen. So you converge in distribution. The backwards process is, the problem is, when you have a Markov chain, Markov property holds in the forward direction. It doesn't hold in the reverse direction. So you cannot get the probability of xt minus 1 given xt. That's not easy to get. And it doesn't always hold that it's just like invertible. So we want to learn the inverse process. So how do we actually sample from the reverse one? Well, let's try base. Right? You take the desired probability, you apply base. There's a problem, right? We need to approximate qxt, and that's very intractable. So we can't do that. Instead of doing that, we will note that during training, we have the clear image, right? We have x0. So we're going to train a generative model by saying we cannot get xt minus 1 given xt, but we can get xt minus 1 given xt and x0, because that's just defined by our property. So if we define the probabilities, as this is not bottom, that's just from the before, it's saying how we can the noise. So we're trying to say we want to learn a network that given the noise image class of t is predicting the noise image or the noise image class of t minus 1. And we say that probability at class of t, like capital T, is just the noise. And we want to learn it by learning a mean and a standard deviation. We're saying my denoising step from t to t minus 1 is going to be, I take some mean at that time step, and I step into some direction that is controlled by my delta or sigma. Sorry. And this gives us a loss that is over the distribution of the noising process, so xt given x0, and it's just the KL divergence between the learned denoising step and the tractable. So what this is saying is our distribution induced by our tractable version of our reverse process to be as close as possible to the learned distribution, or like the reverse. This should be as close as possible. So how do we actually train this reverse process? Well, we want to find like a model, a generative model that generalizes or maximizes the likelihood of training that. We've been doing that all the time. You maximize the log p of x. And as Aditya was doing before, is
we can find the lower bound, and this separates into three terms. One is the reconstruction term, as we said before, just saying, okay, you have to maximize the probability of reconstruction. The other one is the prior matching term, which is saying the probability of the actual noising process to be as similar to as possible to the normal distribution. This, as I set t to 0, t to infinity, this will go to 0. So you essentially ignore this. It's you can see that it's not dependent on any parameters, so it doesn't affect the loss. You know, if you have a loss, you shift it by some constant value, it shouldn't affect your minimization landscape. You just shift the minimization. And then you have the last term, which is the denoising matching term. And this is saying that we want to make these two distributions similar. So as I was saying before, this is just saying the learned denoising set is similar to our tractable reverse process.
So we find the model that maximizes this. This is from the lecture notes. They're just saying which terms are from where. And as I said, ST goes to infinity, that matching term goes to 0. And yeah, this is the denoising matching term. We just learned the desired transition set as an approximation to tractable ground truth denoising set. Yeah. So here we usually use the parametrization technique, saying that instead of predicting a mean and a variance in all the dimensions, we're going to reparameterize it to predict the noise at some time step. So we have a schedule, and at each time step, instead of predicting the mean and the variance, we're just going to predict the noise. And then you can reparameterize your prediction in terms of just predicting the noise in that time. So you're saying, I'm going to denoise my image by taking the noise image as an mean and subtracting some amount of noise that's predicted by this epsilon theta. And this depends on the noise image times the t and the t times the schedule. You can, if you parameterize the loss as well, the denoising matching term goes into an MSE loss. That's pretty nice. And as we said, this gives us that the actual backwards learn process is approximately the same as our tractable reverse process given our denoised image. The training algorithm, I'll just go quickly over this. How you actually train this, you do it until convergence. You sample a clear image from our image distribution. You sample time steps uniformly from 1 to t that we chose. You sample noise, and then you optimize for this loss that we said is just the MSE loss. And what this is doing, you can think about it is just predicting the amount of noise at time step t. And the sampling algorithm is just very similar. You sample from the normal distribution as we said, so we go into the reverse process. You sample from normal, take the time step in the reverse order, so t to 1, sample a z, which is just like a variable, and then we compute this, the denoise version for this time step plus some small noise. Yep. Okay, I'll just skip this. Alternative perspective, I don't think this is as important, but it's good to know. So you talked about the score-based version of diffusion. So we have two ways of doing it. One is looking at it, the process as a Markov chain. The other one is looking at it as predicting scores at each position. Both are equally valid. The latter one, the former one is more popular now, but so the idea here is we want to estimate the probability, P of X, right? The problem here is we don't have the normalization constant. And what the trick here was that we still want to maximize the log probability, but instead of just for maximizing log probability, you can try to take a gradient of the probability, and this gives you, with respect to the beta space, and this gives you a score function, which is tractable. And you don't need the normalization constant because it just goes away because it's a constant, right? So why this is useful? A bit of a side tangent. If you have a score of a distribution and you don't have the normalization constant, then management dynamics can tell us, given the distribution that doesn't have a normalization constant, is non-normalized, how we can sample from it given the score. So what is the score? Well, the score just tells us what direction in space we should move from our current point so that we increase the likelihood of our data distribution. The loss we can get by just minimizing theta or the DKL divergence from before. You will get the same
loss and it's saying you want to predict or learn the score. It's similar to our score with respect to the distribution
of P of X. And sometimes we add the noise because if you don't have noise, you can have like inaccurate estimations of the score. Like as a training, it's fine. So we learned this, cool and fancy score function. It's much better than Markov chain, not really. But what do we do now? Well, as I said, we just take Landry dynamics. You take an arbitrary point in your noise distribution, and you just follow your score, predicted score at that point. You do that continuously and saying, what direction should I step in to maximize the probability of this point? And you just do that continuously, and you get until you reach a mode, and that's your denoised image. Okay, conditioning very quickly. The idea is instead of just predicting P of X 0 to T, you condition on some label Y. This, same rule as before, we just have a conditioning on the individual probabilities at each time step. Similar things happens when you're in a score-based modeling. You have just a conditioning on Y for our score. So what we can do is we take, we do base on P of X, T given Y. We see that this kind of decomposes two terms. One is unconditional score from before, and the other one is again the cellular gradient. And we can use that to actually do like a classifier by the one thing you can do here, we'll see later, is you can add the diameter, which is saying how much do I want to follow my unconditional score, which is saying from here, where do I follow to maximize the likelihood, and I don't care about direction, and how much should I follow some direction that I say, okay, I want to create cats. So we can look at that here. We're saying conditional sampling of the image is the same. Excellent. Unconditional score, which is telling me no matter what do I want to generate, what direction exactly create the best looking image or the most probable image. It's fine. Some term that is saying what direction should I move so that my image is most like my condition, which is giving you a vector. So what you can think about is I have this unconditional term, and I have a vector from my unconditional term to some condition. So it's saying if I'm on some point close to the manager, and I have cats here and dogs here, my conditioning is going to give me a vector towards cats. So instead of just going direct to the manager anywhere one in this term, it's going to go more towards kind of averaging the vector direction one. I think that makes sense. Okay. And to achieve classifier-free guidance so that we don't have to use classifier all the time, what you can do is drop the conditioning term. So you set and make zero sometimes, so sometimes greater to one. So you achieve unconditional guidance. And what this gives you is essentially saying that I will prioritize, condition guidance, but I don't really need the guidance. And this improves quality, but kind of decreases diversity. Okay, this is just saying that the two ways of looking at scores and the Markov chain are equivalent. Any questions? I went through this pretty fast. Okay, now either no one understands anything or everyone understands everything.
Oh, they don't care.
Huh?
Oh, they just don't care.
Oh, yeah, no one cares. That's good. Well, that's not good, but oh well. Well, then problem 2.
Do you guys want to go over the practice exam so that
you have solutions? I don't know. Does anyone have questions about this?
Yeah.
If anyone tried solving it, does anyone have questions about it? If not, then you can just look at the solutions and post them at.
Or we can go over it as well. If you guys want to come up, we'd be happy to go.
Yeah, that's fine too. We will be grinding ahead. So thank you, everyone.
Hopefully this gives you guys appreciation for how good Killian and Jennifer are in lecturing. Yeah.